Very good morning to all.
Good morning, sir.
Good morning, sir.
Respected Anil Kumar sir, with your permission, can we start?
Yeah, we can start. Good morning to all. We can start. I'm ready.
Thank you. I am a Professor Kunal Suthar, Assistant Professor and Head MSc Universe Department. I welcome you on behalf of ISTAR College and ISG Vallabh Vidyanagar chapter. I welcome Dr. Anil Kumar. He is a scientist, engineer SG, and the head of the photogrammetry and remote sensing department of Indian Institute of Remote Sensing, IIRS, ISRO, Dehradun. He received his BTech degree in civil engineering from IUT from the University of Lucknow and his ME degree as well as his PhD the soft computing from the Indian Institute of Technology, Roorkee. So far, he has guided 8 PhD theses and 8 more are in progress. He has also guided several dissertations of MTech, MSc, BTech, and postgraduate diploma courses. He always loved to work with PhD scholars and masters and graduate students for their research works and to motivate them to adopt research-oriented professional career. He received the Vishwaroth Rama Vishwarotri Award for contributing state-of-the-art fuzzy-based algorithm for Earth observations data. His current research interests are in the area of soft computing-based machine learning, deep learning for single-date and temporal, multi-sensor remote sensing data for specific class identifications, and mapping through the in-house development of the SMIC tools. He also worked in the area of digital photogrammetry, GPS, GNSS, and Lidar. He is the author of the book Fuzzy Machine Learning Algorithm for Remote Sensing Image Classifications with CRC Press. If we list his achievement, the entire webinar time is lessened. Hence, I hand over the session to the sir and request to enlighten the participants. I welcome you, sir, and hand over the sessions to you, sir. Thank you, sir.
Thank you, Dr. K. Sudharji, for considering me as one of the resource person to deliver a talk under ISG umbrella at CVM University and ISTAR Institute. And first of all, I would like to welcome all the participants, those who have joined in this weekend because we have holiday, but still they have joined and shown their interest to understand this topic. This topic has been kept at a basic level to further understanding the different level of Lidar technology. Before I go further, I would like to inform I belongs to working at IRS ISRO, which is located at Dehradun. It is a academic institute working under ISRO, and it is conducting PG diploma, MTech, MSc programs in geoinformatics and remote sensing and GIS. MTech is a regular in-campus 2-year program and having 9 application streams, and the PG diploma of IRS is also having 9 application streams in which there are 2 technical department and 7 other application areas. Plus MSc program we conduct with ITC Netherlands, which is again a 2-year program, and parallel to that MSc program we also conduct one more second PG diploma in geoinformatics. So both these geoinformatics PG diploma and MSc geoinformatics program is jointly conducted with the ITC Netherlands. MTech and IRS PG diploma is conducted jointly with Andhra University. So anybody interested, presently applications are on for applying PG diploma and MTech programs as well as MSc and PG diploma with ITC. Anybody can apply. Those who are interested. In all these courses, the minimum requirement is as a qualification, basic qualification should be BTech in engineering stream or master's MSc in science stream with mathematics or computer science or other subjects. You can see in the course calendar and you have to apply online mode only. So that's all about IRS, and now I'm starting the topic. I'm sharing the screen. I hope you are getting my voice properly. And now let me share the screen. Now I hope you are getting my screen also. You can see my PPT. There is no issues. Please confirm so that I am comfortable to know that what I'm delivering is fine.
Yes, sir, it's visible.
So the topic which was given is Introduction to Lidar Technology. Basically, maximum lectures I cover and I enjoy where I have already done work as a project, but more than that, I have done some research also. So in the Lidar domain also, I have done little bit research, not much. My specialization from my PhD onwards developed to drag me towards fuzzy machine learning and deep learning models, evaluating them, how they behave, why they behave, what are the parameters on which they are dependent, and then later on we tried to apply them on crop studies, forest studies, and forest burn studies, or maybe crop stubble burning at different data sets, how we can extract them, and then how it is easily we can do that, and then post disaster assessment at field level, it can be agricultural damage or urban damage, can we do that. So then I'm testing the fuzzy machine learning and deep learning models. So with my vast experience in this area, focused, so I've written the first book with so many pushes came out, and I brought that book for all the society called Fuzzy Machine Learning for Remote Sensing Image Classification, and this was published by CRC Press in July 2020. And after that, I got a taste, and I was feeling to go for one more book. That is very important topic. So it is coming up by March in this year, by the next month, 2023, again with CRC Press, talking about more on integrating the data sets. So let's see. And I'm also going for third book on deep learning. So that is my core area where I basically enjoy implementing the ideas and learning the things for the society. So here I will start the introduction to Lidar technology. So I hope the audience, those who are listening to me, they are a little bit aware, or maybe more, the experts that about the remote sensing and GIS. So remote sensing, if you see the remote sensing image, what it gives you, it is giving the ground as a form of image form, where you have each block, that is pixel, and that is giving you reflectance or emittance from the ground. So it is an imaging sensors we are using in the remote sensing domain using electromagnetic spectrum. But if you go on changing the sensors, one of the example is Lidar, and I remember this Lidar when I was doing my 12th class. That time the Lidar topic introduced in the physics, so I can relate this today with the basic learning what I picked up. So Lidar is not basically the imaging sensor. It is a geometrical sensor. So first difference you have to understand, the Lidar is not an imaging sensor like you get the remote sensing images, you have pixels, and you record the reflectance and the emitted energy. So in the Lidar also we record the reflected energy, but it is not a imaging sensor. And due to the Lidar technology, you got the new technology in the Lidar domain or in the remote sensing domain, and that is called cloud points. Yeah, cloud points. So cloud means is a dense droplets if it is there. So that is called your clouds as a basic definition. Maybe more specifically you can go. Same way there, if you have more dense points, so they are called point cloud data. So that is the geometrical data. It is not an imaging data. Please understand. Now, why the technology has been developed and when it has taken the birth. The technology was ready in 1960s, but it was not ready to use. It was not ready because this technology requires support from other technologies that we will see in the coming slides. So first I would like to talk why people have gone for Lidar. So because they want to go for topographic data representation. When you say topographic, it is a terrain on the ground, and terrain you want to see vertically the height, you want to measure the height. So you are looking the height to be measured, and that is called topographic data. Height can be on the ground, or height can be including a tree or buildings or any other object. So where you are getting the height information, the Lidar is a very good solution. So the application was for topographic data representation. When you talk about topographic data specifically, the first question comes, what is where? That means you want to record X, Y, Z of that point to locate that point. And second is what it is. What is what? Its attribute. Mainly, if you see in remote sensing, we are focusing its identification. It is a forest or water. Even though we locate its XY, but we don't use it Z because Z is not important. Z is our reflectance or the label is forest. XY is the location and Z is the as a field defining it. This is forest. But in Lidar, we are doing measurements where it is in the form of actual three-dimensional information because ground is three-dimensional. It is 3D. So we are recording the X, Y, and Z, and we are focusing on Z. That's the height of the ground, including the objects or excluding the object. So while topographic data, like in the map, you get the contours. So application of topographic data is to generation of contour profile, contour or the profile of the ground or sections on the ground, flood hazard, zoning, and flood forecasting. It is very, very important where we want the slope information. City drainage network, again dependent directly on slope information of the ground. Land subsidence and the land slides, already you can see Josimat is the news for which they require the ground height information if it is changing or not. Then route planning and estimating the cut and fill in civil engineering when you go for alignment change or new alignment, or it can be road or your railway tracks. So there you want to go for cut and fill, again you require the ground height data. Disaster management, maybe like forest fire, military applications in line of sight or view shed analysis. That means from a point how much area is visible to locate that point with a bunker. Or in mobile towers, the company wants to know some peak point on the ground in a city where tower can be put up so that it covers the maximum area and the blockage is minimum. When the blockage is minimum, maximum user can receive the signal. So these are the very important applications where topographic data is required at different accuracies. Need for high resolution elevation data nowadays for modeling floods. Every alternate cities you see the flood is coming up. A few months back we heard in Bangalore, sudden in the zonal areas that the flood was coming up, and people wants to go for disaster management, cadastral mapping, urban facilities management, flood inundation, which area is very, very sensitive for flood inundation, and so that people can take action. This can only know once we have height information at 0.5 meter or better. For infrastructure development at 0.5 to 1 meter, we require contour information, and the base map should be 1:1000 or 1:2500 scale. So here elevation data, you can see the representation of height we represent in different forms. Very common thing we have seen, we represent the height in the form of contour. In the topographic map, you see this height mainly in the contour map, but also you see in the benchmarks also, or as a spot heights. But second thing, with the GIS technology, you can get very easily the digital elevation model, and today it has different names and you get confused. So we'll try to resolve this issue also. Sometimes you see DM, sometimes you see DSM, sometimes you see DTM, and you go on confusing, and there are so many words coming up. You will see this, and further you can see its form of height to be represented as a triangular irregular network. It is a vector data where you can represent the ground in the form of tin, making the triangles, and you join the vertex and you get the height information. It is very good for visual interpretation when you see small dips or small ups and downs in the ground. So tin, on the tin surface, you can see these very small variations on the ground very easily. So for visual interpretation, this surface is very good. You can generate by any GIS software. It is there for it as a part of interpretation techniques. But it is very complex to handle by the software. So that's why you see post-processing, any post-processing you want to do, you don't do on tin, but you can generate tin for visual interpretation. Generally, we do processing on done data, that is your grid, which is in the form of image form. You have grids and you have pixel value, and that pixel value talks about the height information of the area. So here it is in the grid form. It has more redundant pixels, but it is very easy to process. That's why all the processing on dam we do on the grid form, like aspect generation or slope generation. And then we can also represent the ground in the form of contour lines. We can have grayscale image. We can represent these surfaces as a grayscale image or shaded relief or perspective view or 3D view. In a particular angle, you want to see how the ground is appearing and how the slopes are there. So you can easily visualize these surfaces. And in ADAS, you can have virtual GIS tools where you can do the visualization in 3D perspective. So here you can see the 3D perspective and the grayscale. So this is a grayscale representation. And grayscale means wherever it is white, it is the height is more. Wherever it is black, the height is less. Here you can see the leaf shaded relief surface. So here this again gives you this more or less flat surface, but actually maybe water body. And here you can see the hilly terrains and the ridges and the valleys and the streams you can see very easily in this shaded relief surface. You can have the perspective view from different angles. You can see how the ground, the terrain profile it is. It is very important for different applications, more maybe for the defense area or the tower placement and so many other. The water people are maybe looking for how the drainage is in the area to identify the catchment. Then you can also have the 3D view. There are softwares which allows you to see the ground in 3D. Even though it is 3D surface, still using the red and blue images of dam, you can see the ground in 3D. So these are all possibilities there in the current softwares we have. Then orthophoto generation. When we want to correct the image with respect to relief, we require dam height as an input data. A approach of visibility map, like from an area, how much from a point, how much area is visible, to identify that point as a bunker in the military domain, to identify the same point for putting the mobile tower or TV tower or radio tower, so that from the tower the signal is propagating to the maximum area and there is a minimum blockage. So this is very good to use the energy to the maximum area, and wastage of energy is very minimum. Then profile determination of the ground, volume determination. In the mining, it is very, very important to monitor how much open cast mining is going on. So daily basis, if you scan in the morning and evening, if you take the difference of it, you can find out how much excavation has been done in the open cast mining. If there is no, and then you can monitor the illegal mining also. Generation of slope map, slope models, it has different applications in water resources, in agriculture, in soil erosion and so forth. It has very strong application. Urban planning and utility planning, again you can do. Then perspective representation of the ground and 3D GIS and so forth, other applications, it is there. So dam resolution. Now coming to resolution of the dam, this can be in the two forms, like horizontal resolution or maybe the precision of it, right? So here if you see, like dam is of 10 meter, same area, dam is of 30 meter. Now you can feel how the information is coming up. The small undulations are very seen nicely here, and here it is more or less dissolved when the picture is going 30 meter. That means this is giving less information compared to more detailed information you can see at 10 meter. Then if you see the effect of horizontal resolution effect on dam, it decreases the horizontal resolution products, it is produced like low slope gradients on steeper slopes. So you will see low slope gradients on the steeper slope. That means steep areas will not look so steep on an area. The steeper slope gradients are flattened if the resolution of the image or the dam is decreasing. Then narrow range in curvatures, large catchment area in upper landscape position you will see, and lower catchment area in lower landscape positions, and leads to loss of small scale features. When you have small detailed information which get lost when you take the larger pixel size of the dam. Then you can have the horizontal resolution here in the form of, if this is the actual ground and if you are taking vertical points at very small spacing here, then you can see it is representing the ground as it is present on the ground. The moment you decrease or increase the point spacing, sampling point spacing, you can see how the ground is appearing. So here you can see it is showing more steep in this area. Actually, the steep is gradually changing. So that effect is not coming here. Then if you further decrease or increase the point spacing here, then you can see how the ground is represented. So you can see if you start basically increasing the point sampling spacing, you can see the information is decreasing. So in the ground, there is no method. We have to take very densely populated high points to represent how the ground is. We should always remember the ground is a very irregular surface. There is no systematic change on the ground. It is very irregular. So for that irregular, there is no any systematic process to take just one point and represent the height of a city. You require very dense millions of points to actually represent the height. So it all depends what is your application. According to the application, you can decide the point spacing and then go for measurements using different technologies to get the height of the ground. So here, second thing, if you reduce the data reduction, like 100% points are there. If you take 50%, you have quite a half point. Then it's just 25% points, then 10% points, and then 5% point, and then just 1% point. So what I want to specify here, because ground surface is very irregular, just with few points you cannot represent the height information. You have to see application. Does 1% point taken in a city is enough to represent this height, or we require large number of points? According to the application, we have to decide which technology we can use. We can go by GPS, we can go by total station, we can go by stereo data, we can go by there are so many sources which I am going to talk about, but you have to decide as per the application. Then we can see. Then you can see the dam as its precision with respect to the height, how much accurately the height is measured, the precision. So here you can see error in height is 0.1 meter, and here you can see error in height is 1 meter. So when the error is more, you can see more spikes. So here you can see unwanted spikes which are making you confused that ground is undulating there. Actually it is not. It is very smooth in this area. Even though slope is changing, it is increasing, but it is not very zigzag. But if you see 1 meter precision, that is quite poor. You will see more spikes and the dam. And this information you can see when you have processed the different stereo data, stereo images to get the dam. Images which are having very good orbital information, the dams are very, very smooth. Even though you are not adding any ground control point, still the dams are very accurate. That's the one example I've shown to feel these spikes in the dam. Now, vertical precision effect. What happens when you have the precision very good of 1 meter or better, or very poor, say this of 1 meter, so 0.1 meter as a better precision, or maybe 1 meter quite poor one. So what happens if you change the precision of the dam? When you're decreasing the vertical precision, then what happens? You have more flat cells, more steep cells are also coming up. A wider distribution, the curvatures is there. Discretization of elevation values, which leads to discretization of other terrain attributes and reduces the similarity in the data set. So these are the effects when you decrease the precision of the dam. The dam vertical precision effect, here you can see when we are sampling with very high precision, you can represent the terrain as it is there on the ground. But when you take its precision is quite poor, then what happens? The ground is appearing like that. Now here you can see a lot of zigzag, and these zigzag gives you a lot of spikes in the dam. Now, a conventional way of data collection of the terrain, very previously people were going with aerial survey as an aerial photogrammetry. That stereo photographs are used. As a stereo photograph means two photographs taken from two different angles for the same area, and they introduce parallax. And due to parallax, they can convert this information to the height information. When the satellite came into picture, people have used interferometry as a spaceborne or airborne. Land surveying using total station or plane table or theodolite, they can generate the contour information, and they can produce the terrain information. Nowadays, satellite-based navigation, that's called GPS. It has been changed further. It is called now GNSS. Why GNSS? Because today you can use the satellite from different navigation constellations, and you can get your height and XYZ coordinates from navigation satellite data. So that's why with time the GPS technology has been changed. Now we call it as global navigation satellite system. That means we can use the navigation satellite of different constellations anytime, and we can get our coordinates on the ground. Overall, if you see the source of dam, it can be from ground matter, as I told you, by GPS or by theodolite or conventional surveying. Photogrammetry means the stereo photogrammetry we can use. Then Lidar means which I'm going to talk today. Then ISRO, that is SAR interferometry approach, you can get the dam. And UAVs, again UAV can be on the aerial photography, it is there, you can use this data, or this can be on the Lidar. Again, Lidar is changing the platform from different area, which again I will cover in the coming slide. So the conventional way of data collection, one is land surveying. So you can see some of the issues in land surveying. This is very time consuming. You can work in daytime, not in night time. Inaccessible area is quite difficult to work. The area where you cannot work, it is not accessible. Not possible in very bad weather conditions or fog conditions. You cannot work with the conventional surveying. Generally, cannot be done in night time. So these are issues when you work with conventional surveying. It is time consuming and so forth. Conventional way of data collection, again, if you focus on aerial photography, so what are the issues? Not possible in areas like in forest, desert and coastal areas, because here the ground is either covered by vegetation or it's very homogeneous, and due to the homogeneous, or by the, if it is homogeneous, you cannot get the ground control points which is required to process the data, and if it is covered by forest, again you cannot get the ground height, and you require the GCPs, that's ground control points, to process the data. So we cannot collect number of times in the desert, because desert is very homogeneous, there is no object, it is only sand, sand and sand. Same on the coastal areas, you see only the sand dunes around the coastal regions, you don't see any object to collect the ground control points. Again, it's an indirect method, means directly it does not give you height, you have to do processing of the data, which is an indirect method, and that takes time again. Not possible in bad weather conditions. If it is windy or if it is raining, you have to avoid the flying, and again it depends upon sunlight. In night time you cannot do aerial photography, it is a passive sensor. Then coming to GPS, it has its own issue. Time has to be occupied to observe and measure, cannot be done in inaccessible area like in some other country area, or if it is covered by water body, it may be difficult to work. If there is transmission lines, again it does not give you very good accuracy, because there is magnetic flux which introduce the multi-path in the signal. Cannot be done within forested area, because it is covered by a forest canopy and signal is not coming to the antennas, and you cannot again get under forest areas. Talking about satellite photogrammetry, people have started this spot sensor, it was a stereo sensor in 90s, and then Indian data, IS-1C, 1B, again it was stereo data. Nowadays you have Worldview series, commercial satellites, ComSat, Korean satellite, Pledis data, you can use it with very high accuracy from Worldview, ComSat and Pledis. I use these data sets, they provide you very good accuracies to generate the dam. But again, their accuracy is not up to the mark what we are looking for urban planning or other areas. They require still few GCPs, even though we are using orbital parameters, but still they require minimum GCPs to define the dam accuracy. And it is satellite availability is also dependent. If the satellite is not available on that area on a particular day, so we cannot get the height information on dam of that area. Interferometry, it has more or less same issues like the satellite stereo photogrammetry data. It is again spaceborne or airborne. It has less accurate airborne systems, gives 1.5 meter to 5 meter accuracy. Cannot see under canopy. If you are working under forest, again you cannot get the height below forested trees. And spaceborne depends upon satellite availability of that area. So these are limitations of this previously well-established technology, which gives you the height information in the form of dam. So platforms, if you see for Lidar, how we have changed specifically, it can be a TLS ground-based terrestrial laser scanner, which we already have in our campus from 3 brands, from Leica and Sokia and other companies. Then you can have the Lidar UAV based. It's the latest trend coming up in India. People are developing and having these concepts also. Then it has gone to this is the case of airborne Lidar, which was authorized to be captured by data through NRSC Hyderabad, one of the center of ISRO. And here this is the concept. You can see it's an aircraft, one rover GPS is kept here, and one base is kept here. And we'll talk about how to capture the data through airborne. And with time, like 15 years back, NASA, JPL thought to have satellite-based LIDAR technology as a satellite LIDAR, not for ground observations. Their objective was to study the ice sheet depth measurements at the poles of the Earth, as well as snow cover studies they want to go for. But people sitting on the land, they have used this ISAT glass data for ground studies also, maybe in forest. I also tried the spaceborne data to improve the accuracy of stereo cartosat data. And airborne data I used in the urban area to map the buildings with high accuracy, find out the area, parameter, and generate the bare earth DM. I'll talk about what is bare earth DM. And I also use the airborne LIDAR data to map the forest area to find out the forest canopy, forest height, and other parameters of the individual tree. So airborne LIDAR data, if you see the technology, the topography, this is mainly developed in this area for topographic data generation, and it is basically using the again speed of light in the form of laser light. So that's the one difference. It is using the laser light. Comparatively technique, it is eliminating the several limitations of conventional methods. Technology known by different names today. It is called airborne altimetric LIDAR. It is called laser altimetry. It is called laser range finder. It's called laser radar. It's called laser mapper. Laser radar is mainly used in the concept of satellite when it is using the laser light. Why the laser light was chosen? Because if you take out the 12th physics book, as I told you when I was in the 12th, that time the extra one new chapter came up, was introduced in the physics book, laser. So from there I can recall its properties of the laser. It is very coherent energy, and it is very concentrated energy. So coherent means, and its divergence is very less. If you take a table lamp and if you project it on the table from a distance, you will see the table lamp is giving this much impression on your table. So its footprint is very large, and energy is not concentrated. But same thing if you do your pointer, what you use in the delivering the lecture on the board, if you put it the pointer on the board, it shows you single dot. It is not diverging to the very large area. So it is very, its divergence is very less, and this is coherent energy. For these two properties, this has been considered in the LIDAR technology to use for measurement purpose. So if you see the sources by the elevation data and their accuracies from ground based, you get a consistent less than a centimeter level of accuracy. From LIDAR, you can get around 10 centimeter depending upon the flying parameters. From photogrammetry, you get best around 30 centimeter accuracy in the height. From ISRO, you get the height accuracy of 2 to 5 meter. But if you are flying through LIDAR based UAV based LIDAR, the accuracy will be again in centimeters. So this is the level of accuracy you can achieve by different sources in the context of height information. So presently with these different sources, you can get the map at different scale. If you have a South India 1:50,000 scale map, their contours are 20 or 40 meter or sometimes 100 meter in the hilly terrain. Their level of accuracy is 1/4 to 1/5. What does it mean? If you divide 20 by 4, it comes 5. So accuracy in the contours is 5, or here it is 4 meter. So 4 to 5 meter are your contours are accurate because they are generated by approximation method. If you are going for SRTM DEM, which is freely available data at 90 meter pixel size, so its accuracy will be 8 to 10 meter. If you are going from cartosat DEM with 20 meter by 20 meter pixel, its accuracy will be 4 meter. If you are going with airborne 1 meter by 1 meter pixel size, you can achieve the accuracy of around 15 centimeters. And if you go by UAV based LIDAR, you can achieve the accuracy of around 1 centimeter. So you can see the level of accuracies from the sources, and from Lidar, its high accuracy is very accurate compared to the other sources. So this is the just first some point I just covered to introduce the Lidar and the other conventional techniques on Lidar technology. Any questions if you have, you can ask now, or you can maybe keep the questions later. Second part of this I'm talking about, just see the time also, just have to go by 11:30, and I've just crossed 30 minutes. So next is laser and the laser scanning. So now we can go directly in the Lidar technology, how it works, and understand what is lasers and laser scanning. From the name itself, you can see it is using the laser light. Generally, it's the wavelength if you see in the laser light, it is having the two areas. Either at its wavelength is 0.5 meter, 0.5 micrometer, sorry, micrometer for bathymetric information. That means if you want to study water bodies depth, so you have to go for 0.5 micrometer for bathymetry, and it is around 1.04 micrometer for topographic mapping purpose. For ground measurements, if you want to do, the system will have the wavelength of around 1.4 micrometer, and if it is used for water depth measurements, its wavelength will be 0.5. Because why we are changing the focal the wavelength from 1.04 to 0.5? When you go for water body studies, the water will absorb the wavelength of NIR, that is 1.04, which is an NIR region, then it will be absorbing, so nothing will come out to the sensor. So wavelength is used at 0.5, which is very reflective for water. You can see in the reflectance curve for water, it is giving maximum peak reflectance at 0.5. So this way, there are two types of sensors as per the wavelength. So laser is basically light amplification by stimulated emission of radiation. Amplification, that is sudden, because what is here, you can take a tube where there are normal particles, they are charged up due to heating or some other process or some chemical reactions, it can be. So these particles are giving the heated up, or basically the electrons goes to the higher orbits so that they release the energy, and that is called amplification by stimulated for a very short time. Very short time, these particles are heated up so that they release the concentrated energy, and that energy is channelized in one direction. So there is coherent, and that becomes your laser light. So its properties is monochromatic, emits in a very small portion of the spectrum. Its width is very small. Intensity is very intense. You can see the application of Lidar in medical science. In sometimes if you go for your teeth, some issues, they say we are doing laser-based bloodless operations. So, right, it is used in medical science. It is used in mechanical cutting the metals. That is very intense energy. Is very quite harmful. Laser is safe. It is safeguard. Its wavelength is safe to the human beings and the other creatures in this world. In your total station, and also it is used, so it is not harmful to the skin and eyes. Then directionality, it is emitting to defined direction. There is a property again for laser, and coherence. It is emitting light only to one phase. So due to coherence and due to its directionality and the intensity, it is used in laser technology. Stimulated emission, I talked about this. I will not cover much. And you can see this laser light is generated by different sensors having different properties. It is generated through gas. It is generated through solid state using different materials, rubidium and other. It is generated through liquid also, and it is generated through chemical and nuclear. So through different forms, this laser light is generated in the different laser sensors. Mainly, if you see, this is very important for ground-based people studying and using the Lidar light. Its reflectance, if you see the reflectance of different objects, here you can see this is the region where the topographic data or the Lidar is used, and here at 0.5 you can see for water. It is sufficient reflecting the light, so it is very good. So for bathymetric purpose, the wavelength is 0.5. For topographic studies, the wavelength is around 1 or 1.5 micrometer. Or this is a nanometer, you can say 1.5 here, micrometer. Now just try to understand the Lidar concept, how it works. Basically, if you take airborne or ground-based or UAV-based or satellite-based, it is basically here the light is transmitted from there are two sensors, one is transmitting sensor and one is receiving sensor. So this is transmitting the light and it is hitting to the object or tree in the red form, and the black one is the reflected back, so that is recorded, right? So once the light is transmitted and reflected back, what you have noted down, you have noted down the time. So here if you take the T by 2, here if you take T by 2 and then multiply by velocity, you can find out the range, direct range, you can find out. That's one. You can see its footprint is very, very small because its divergence is very, very less. You can note down when you fire the laser beam on a board while giving the lecture, you see it is still showing the dot point on the board. If you project the table lamp, you see its area coverage on the table is very large, so its divergence is very, very large. But here you can see its divergence is very, very less. It is talking about at some elevation. So from at particular elevation, its divergence is of maybe of radians or fraction of radians part. So here you can see it is divergent milliradians, 0.25 to 4 milliradians only it diverge here at the footprint. Then the basic, as I told you, the beam is fired from the source, and whatever energy is reflected back, if it is stored by the receiver, then it counts how much time is taken. Because there is a clock here, when the pulse is fired, clock is started. When the pulse is received there, the time is counted. It is taken T by 2, half distance, and multiply the light of the velocity. So velocity of the light, and then multiply, and you get the range here, R. And the velocity of light we know approximately, this is given exactly, but approximately 3 into 10 to the 8 meter per second. Now here create the laser pulse. So here what is the sensor is doing? It is creating a pulse. It is firing the pulse on the ground. It travels through the atmosphere and interact with the object. Now travel back to the sensor and processing the return signal. So this is giving you only range, which is half information. It is not actual height information of the ground. It is giving the direct distance, and direct distance is not the height of the object on the ground. Here just still I am trying how this Lidar works and what it does. Lot of energies will be diffused, but whatever energy has gone back to the sensor, if it is having sufficient energy which is going to the sensor, it will be recorded by the sensor. If the energy is quite weak going to the sensor, it will not be recorded that information. So here you can see there is threshold by the sensor. If the energy is more than this line, more than this threshold, it will be recorded. Like this is your initial fired pulse, it is this much. So this will be recorded, this will be recorded, this will be recorded, and this will be recorded. If there is a pulse is only this much, this will not be recorded because it's not beyond the threshold. So here, if you count this 1, 2, 3, and 4, there are your first pulse here, then second pulse here, and then third pulse. So what happens? You can get the multiple returns. You can take an example. If the pulse is fired on a flat surface, then what will happen? The beam is going to the surface and going immediately. The complete energy is going back. So you get only one return. But second case can be like a tree fired from an angle. Then what happens? Some energy is reflected from the top. Some energy has gone to this branch and again fired. So this is going from here. So second, some portion of is hitting here and going back, and third portion is coming here and going back. So what is happening in this case? You get 3 coordinates of this is the first point, second point, and third point. So this now you have 3 returns, and this is called multi returns. So this way, from single pulse, what is fired by the sensor, you get 3 returns. This is very important. In some cases, like in buildings or trees, we get the multiple returns. then layout of these points depending upon the mirror, because when the pulse is fired, I hope you're getting my PPT and voice uninterrupted. Please, can you confirm?
Yes, sir.
Okay, thank you. So then on the sensor, what is happening? Sensor is somewhere here, it is firing the pulse. It is firing the pulse on the mirror, so that the objective of the mirror is to spread these pulses into different areas. So you may have the flat mirror, so on the ground you get a zigzag pattern. There can be circular mirror, you get a more or less parallel patterns or circular patterns like this. So this all depends what type of mirror we are using in the sensor, and according to the mirror type, it is a flat bite or it is a circular one, you get different patterns of points on the ground. So these red dots are the pulses. That's why I told initially, this is not an imaging sensor to give you image. It is a geometrical sensor. So on the data you will see point data, like in GIS you have point, line, polygon. So it is a point data where you have for each point X, Y, and Z. So on the ground, if you see the layout of these points, these red dots are giving you height information of these points. So the pattern can be like a jet pattern or parallel pattern, or it can be circular also. Now here you can see the pattern is in the circular form. Here you can see it is firing the beam, the mirror is rotating, and due to the movement of the mirror, the point is spread from here to here in a bigger area. So in the y direction you see the point spread. So here you can see in the y direction the point spread, and in the y, so this is your y-axis towards x-axis, the aircraft is moving. So you get the movement in this direction due to the aircraft movement, and this side due to the mirror movement, the points are spread in the swab. So you get all the points in this area also and in this area also. Both way you get the movement and you get the points. So you can have the patterns like sinusoidal wave, or depending on circular or jet shape. It all depends how the mirror is there and how it is rotating on the sensor. Now here you can see one more important thing: scan angle. What angle we are choosing, because it is half angle. If you are firing, if the aircraft is going like this, it is firing in this direction also. It is firing in this direction. This is the total swath it is covering. So if you make it half, this is your theta by 2. So this complete angle is your theta, and this you make it theta by 2. So here these angles are your half scan angle. So half scan angle can be 10 degree, can be 15 degree, 20 degree, 30 degree, and 37 degree, or maybe more. Overall, it is going range from 14 to 75 degree angle we can take. If you take both the sides, if you make it half, then half is shown here. So again, just I've given you a little idea about the how this laser independent is working, and what we are basically getting from Lidar is the range information, and range is still not complete information, and that's why I told you one more statement. This technology was there in 1960s, but it has not taken the birth to use in the Earth observation area. In 90s, when GPS came, it has become fully operational to use it and achieve very high accuracy. Previously, they were using IM, inertial navigation systems, which was supporting. So this other technology was supporting the Lidar technology to get and use it. So in my third slide, I will show that how this has been happened. Actual airborne Lidar technology. So here in this diagram you can see now more clearly, it is not only range, you require the role of GPS in the form of DGPS. So this is your base station, and here you have rover which is working in DGPS mode, and here you have IMU, inertial navigation machine, which is giving you directions of the beam along X, Y, and Z, or pitch, roll, and yaw. So this is giving you range from the laser sensor, but the laser sensor itself is not sufficient in Lidar technology. Why? Because you want the coordinates of this point. How it is possible? That is only possible to know in which direction this beam was fired. So direction will know once you are using inertial navigation system. Inertial navigation system is a default system in aircraft which helps the pilot to know in which direction the plane is going. So it gives you 6 parameters. One is X, Y, Z, translational coordinates, and your pitch, roll, and yaw. Roll, pitch, and yaw. So these are your translation coordinates and these are your rotational coordinates. Rotation about X, Y, and Z. Direction, we can say direction. So when the pulse is fired with the help of roll, pitch, and yaw, we can find out in which direction the beam was fired. And the roll, but what is happening with INS, inertial navigation system, it's this. Hello? Yeah. अभी मैं बिजी हूँ बाद में विल कॉल मी आफ्टर दैट. So here through IMO we get 2 parameters. One is translational XYZ, second is rotation. So in the rotation with time its accuracy is very high, but with time the accuracy of XYZ is not very accurate. So what happens if the error introduced in XYZ? So we are not comfortable to use XYZ after some time because errors has been introduced in XYZ. So that's why INS was not sufficient to be used to get XYZ and pitch, roll, and yaw. Pitch, roll, and yaw is giving direction in which direction this beam was fired, and then XYZ tells what is the position of this laser sensor. Because in surveying or in remote sensing we work from known point to unknown point. So this is our known point. So we should know the coordinates of this point. So that is only possible if I use inertial navigation unit, but its XYZ is not accurate with time, so we cannot accept the accuracy of XYZ. Or even though its pitch, roll, and yaw is very accurate, still we are using it. So people have thought to use GPS, and GPS came in 90s. That's why in 90s the Lidar got full berth to be used on land and water bodies. So GPS, with the help of GPS using base on the ground and rover on the aircraft, we can get very accurate XYZ coordinates of the aircraft every per second or less than a second. So by laser we get rho, direct distance. From GPS we get the very accurate coordinates of the sensor, of this laser sensor. Even though GPS is kept very far on the aircraft, there is offset on the aircraft. This offset we calibrate before flying. How much is the offset between GPS rover and the laser sensor? Plus IME is kept somewhere here on the nose of the aircraft. Again there is offset. So this offset is also calculated. So now we get here three data. One is rho from laser. Then we get pitch, roll, and yaw from INU or INS, inertial navigation system. And from GPS we get very accurate XYZ. XYZ is the position of the aircraft or position of the sensor rather at particular second time when the beam was fired. This gives you in which direction the beam was fired, and this gives you direct distance from laser sensor to ground. Integrating these data sets, we get actual ground coordinates on the ground. So this way the technology got birth with the help of GPS, and in the 90s GPS came, and after that people start talking about Lidar technology. So here the laser scanner mounted in the aircraft emit laser beams with very high frequency and receives the reflected beam to get the range. The time difference between emission of laser beam and the reception of the reflected laser signal is recorded to get the distance, that is again range. And high frequency rotating mirror placed in front of the laser converts this laser into a laser scanner. So here when there is a mirror here, so what it does, it strikes the point across the direction of the aircraft. And the aircraft is moving in this direction, the points are spread in this direction also, and points are spread in this direction also with the help of mirror. So that way this complete area is covered by the laser scanner in the form of points. So inertial measurement unit, which is there inbuilt in the aircraft or in the helicopter, It is giving you XYZ and pitch, roll, and yaw. The measurement is very high, around 200 samples per second you can get, with very high accuracy of 0.005 degree. Works on the principle of laser gyros. It is there, an accelerometer. Gyros are basically floating magnetic pieces in this machine, and in the XY direction, which tells you how much is the rotation in XY and Z direction, and the accelerometer tells you the delay, and that gives you XYZ coordinates from a reference point. But it drifts with time, and again you require initialization of XYZ. So that's why XYZ is not accurate through accelerometers, but gyros gives the very accurate rotation parameters in the form of pitch, roll, and yaw. Since INS is not giving very accurate coordinates, so it was replaced by GPS. And in GPS, people have used DGPS method. DGPS, you can say it is your kinematic post-processing method to get very high accuracy of the DGPS method to get XYZ coordinates. So here, if you are covering very large area, so you can have large number of base stations every 40 kilometers. You can have base stations. Between two base stations, you will keep the distance of 40 kilometers, because to fulfill the common error up to, say, this is talking about one base can be used up to 20 kilometers. To have the common error, you can apply from base to rover. Same way here, 20 kilometers. So if you are mapping a corridor, every 40 kilometer one base unit is kept, and rovers are there on the aircraft. And IMU is giving you pitch, roll, and yaw. And by GPS, in the BGPS mode, you are getting the coordinates of the sensor when it is moving. So you can see it's telling around 25 kilometers. We can keep the distance of one base station can be used. So you can see the laser is firing a beam here to get the coordinates, and we have a GPS to get the actual coordinate of the aircraft, and we have a INS to get the rotation parameters of the beam. So here, to calculate the coordinates, we have to use all the information. One is here 3D ground position. We can calculate to get the location in the form of latitude, longitude, and height. And how we get when we use the attitude, that's roll, pitch, and heading of the aircraft from IMU, range, scan angle, as well as the ground coordinates. When we integrate these data, we get the 3D ground points. So just laser sensor is not enough. We require GPS and IMU also. So now you can see more clearly the fundamental of multiple return technology. When the beam is fired on the flat region, you get a single return. The complete beam is going to the aircraft. You get a single return only. But here, if you see, the beam is hitting here. Some portion of beam may come here, and some portion of beam may come here. So from single beam, you are getting 3 returns. And nowadays the sensors are capable to record 5 returns. Advantage is from single beam you get coordinates of 3 different points on the ground. And in the case of forest, once you get multiple points at different height within the tree, so it is easy to map this tree height also. Not only the ground height, you can measure the tree height also. So again, you can see the multiple returns. Some portion of the beam is hitting here and going back. Some portion here hitting here and going back. Some portion hitting on the ground and going back. And that gives you multiple range returns from a single footprint laser beam. So number of times it has an application to consider the first return and the last return, and we can ignore the intermediate returns depending upon if this is the initial signal start pulse from the sensor. This is the first return, and the range one. This is the second return with intensity 1. This is the second return with second intensity and second range, and this is the third one. So you can see, as per the intensity, we can find out 3 range. If the intensity is not acceptable, is not more than the threshold, that pulse will not be considered. But if it is more than the threshold, it will be considered, and that will be recorded. So here you can see we can get the 3 range values. So airborne laser survey is useful for all or some of the features below. One is a dense array of elevation points that is required. When you require very dense points array on the ground, the laser airborne laser is very important for that. Ground and non-ground features to be measured, like when you want to measure the height of a ground as well as the height of a tree, then it is very useful. When you want precision or accuracy of around 1 meter, 0.5 meter, 0.1 to 0.5 meter, the Lidar is very suitable technology. Photogrammetry cannot work under dense vegetation cover. Quick turnaround time. It is a direct measurement technique. From photogrammetry or from ISRO, it is an indirect method. You have to capture the images and then post process. But here, the moment you get the range, within 5 minutes you can integrate the radar data, GPS data, and the IMS data to get your point. So it is basically direct measurement technique to get the ground coordinates. Then sizable project, like when the area is very large, you can process within small time. Inaccessible area, you can simply fly and get the height. You can work day and night because with the active sensor, you can work day and night. So these are plus points of Lidar technology compared to the conventional technology which I talked about previous slides. Advantages: its accuracy is very high. You can achieve accuracy of around 10 centimeter with airborne. From UAV, you can go around 1 centimeter or better. Easy to deploy. Within a few minutes, you can capture the data. Day and night, you can work. Rapid data collection, very quickly you can get the data. And very easily you can have the digital camera also. You can break the digital camera in photographs on the dam to see actual objects present on the ground. Even though when the data is very high resolution from the lidar, even though it is a point data, still you can get the actual image type of effect on the data. Advantage of lidar: it is of very high accuracy. As I told you, its accuracy goes from airborne 10 to 15 centimeter in height. In XY, its accuracy is less, 30 to 50 centimeter. This is the only technology where height is more accurate than XY data. Like in GPS, XY is more accurate than height. So there, if the error is sigma, so error in Z will be 1.5 times of sigma. But here you can see it is reverse. Height is more accurate than XY. Why? Because when the sensor is recording direct distance, that is recorded very accurately. But the mechanical limitation of the sensor cannot be actually mapped, and it gives you some delay, and that delay introduces the accuracy or error in the horizontal accuracy. Fast acquisition and processing. You can cover very large area, say 1000 square kilometer in 12 hours. And done generation of this area within 24 hours. So overall, you can see in 3 days you can get the data. Minimum human intervention or dependency is there when we are acquiring the data or when we are processing. In processing, you have to just feed 3 files: your range file, GPS data, and IMS data to get your ground coordinates. Data can be collected in day and night. With a slight weather, it is drizzling or a little bit cloud, still you can fly and get the data. Advantage of lidar: canopy penetration in dense forest. You can use it. Some pulses will hit to the tree and they will go to the ground to give you the ground height. Higher the data density you can achieve. Nowadays there are systems they can fire 1 lakh pulses per second. Initially it was 5,000 pulses per second, but today you can fire 1 lakh pulses per second. More than 24 points per square meter you can see. Multiple returns you can collect from 3D. Nowadays there are sensors, they can record 5 returns maximum. DCP is independent. Hardly you require DCPs because you have to only put DGPS at some base interval. That's it. You don't require much working with GPS data. Digital compatibility: the data can be taken in ASCII format nowadays or any shape or any other GIS format, and you can convert and you can process that. But actually the data is in LAS format. It's a file format. You will see the raw data is coming in LAS format because it is very high volume data. So only LAS format supports, and it has an initial information that it is a first pulse or second pulse or last pulse or intermediate pulse is there. Plus XYZ coordinates are also there. Additional data, sometimes you can record, you can extract the reflected image from these data sets, but not much useful. Of course, cost. Comparative studies have found that lidar is cheaper in many applications. Already, if you have hardware, like if you're talking about ground-based or UAV, if you have already have hardware, the hardware initial cost will be large, but operational cost will not be so much large compared to the previous conventional technologies. Lidar strength, it is very fast survey for large or long objects can be done very quickly, requires only one known point as a base station on the ground. High point density can be improved at the border accuracy which you want in the cities, reaches the ground despite coverage like in the case of forests or streets between buildings where the buildings are very narrow. It is difficult to map by GPS or by conventional techniques, by aerial photographs, but still by Lidar you can map the narrow streets like in India. If the weather is not good, perfectly good, still you can use it, and in inaccessible area, it has very good strength to work. Disadvantages: initial instrument cost, it can be sensor, or if the platform, it can be airborne, UAV based or satellite based. Satellite is basically particular agencies is launching, but for airborne or for UAV is quite costly initially to get the system. Spectral data is quite poor because this is not spectral data, it is basically geometrical data to give you XYZ coordinates on the ground. Requires additional spectral or video images if you want the spectral information in the form of images. So you have to mount the digital camera also with the laser or the Lidar sensor. The data is quite large. The moment you decrease the point density, the data becomes more large. However, better devices are available to process nowadays because higher machines are there, so you can still take care. Precaution while flying, because we have to keep the laser light to be of safe mode, so that it should not harm the human beings on the ground or the creatures, birds flying in the air. No possibility of locating GCPs on the accuracy analysis, because here we don't see the GCPs, and that is not required. So one way we can say disadvantage, but it's not required to locate any GCPs on the Lidar data. Does and don'ts, if you see, it provides, here we can see it provides a high density point, high accuracy spatial data. Maybe this slide from touching the link. It is auto rectified, we can use it. And software, there are plenty of softwares which we can, some softwares are free to give the basic processing of the data. Nowadays from the Google you can search a lot of free Lidar data if you want to learn and process the Lidar data. Some of the things if you see on the Lidar, on the aerial photographs, you can see the edge of the buildings is protected. In the case of Lidar, when the density of point is less, you can see the edges are getting dissolved. So they're not so sharp. That is one limitation of the Lidar. The edges are getting dissolved. Again, Lidar difficulty, you have to keep the one base station at every 25-kilometer distance so that accuracy of your actual coordinates of the aircraft maintained. And weather conditions should be still acceptable, not to be very poor. And flight performance, the aircraft should be very stable. It should not give any jerk, so that three instruments what we have kept on the aircraft, it should not get disturbed. Mainly the offset should not get disturbed. This I've already talked about. One more thing, if it is a horizontal, like for TLS based, if you're going for horizontal field of view or vertical field of view, here you can see as per the height, if the height is increased of the laser sensor from ground to air, you can see how the accuracy is decreasing. At 1000 meter by different sensors, this much level of accuracy, around 2.2, that means 20 centimeter you can achieve. If it is going further, applying height, the accuracy drops. That means your field of view is more. So here, if your flying height is 100 meters altitude, you can achieve an accuracy of 5 centimeter. If it is 500 meters altitude, 10 centimeter. If it is 4000 meter altitude, you can achieve the accuracy of around 25 centimeters. This is more important to understand the sensor. What are the sensor property we can have? Basically, the how much height we can achieve for flying. Like you can fly from 200 meters to 4000 meters, and the field of view of these sensors can be of 10 to 75 degree. That's view angle. Scan rate, you can scan the mirror scanning frequencies 1 hertz to 70 hertz. Pulse rate, how many pulses you can fire, that's 22 to 55 kilohertz, but it has gone to now 100 kilohertz. That means 1 lakh pulses you can fire from the machine. Multiple targets, how many returns you can record. Previously it was 3, nowadays you can record up to 5 multiple returns. Intensity mapping, in some case you can record the intensity also, which is from the energy coming back to the sensor. Compensation rate up to say 75-degree field of view. Here wavelength, you see this one indicates this is your topographic data, topographic sensor, which is can for land. If it is bathymetric, here this will be 500 nanometer. IMDF frequency, you can record 200 points of your pitch, roll and yaw. GPS can record 2 points per second. Power of this is around 4 watts. So there are few specifications about ALS like a Lidar sensor. This I will skip. Some of the things I can talk about the application part before I wind up, so that you really feel where the Lidar can be used. General applications, and maybe before that I can give you flood simulation. You can see, you can appreciate if you have the importance of very high data. If it is like every 1 meter how the inundation is going on, if you have the data, you can see, you can do study which area is more sensitive for inundation and how to protect. This simulation for New York City. So these analysis you can do for your own city also once you have the dam of very high accuracy. Now we can see the applications of Lidar for flood areas. I told you it has very strong applications for cities. Nowadays there are very high flash flood is coming up due to the heavy rains for a very short time, and that gives you flash floods. But it is not a problem of very heavy rains coming up in a city due to climate change. More important thing is, do we have very good drainage? We just forget the importance of drainage. People think rains are happening once in a year. Why to put so much investment for drainage? So if you don't have proper slope and drainage in a city, that definitely the city will suffer for the floods. We have seen in the case of Bangalore or other areas also, it is happening very frequently. So this data is very, very important for flood analysis in the cities. Coastal areas, we can map the coastal boundaries, and there also we can go for flood management and the erosion monitoring if you have the very high resolution data. We can have the bathymetric flying in this area, and we can map the sites and their sensitivity for flood management and the erosion monitoring. Generation of bare earth DM. This is very, very important. Initially I told you there are few terminologies for like dam, and we get confused. Dam, then DTM and DSM. So here you may get confused what is what. Actually what I'm talking about is dam, and then second word very nicely explained by in Lidar, that's called bare earth DM. Bare earth dam. So here if you see, if you have a height data where you have the height of ground, you have height of buildings, you have height of trees, you have height of bridges, then it's called dam. If you remove the trees, building height, and the bridges, the man-made or the natural objects on the terrain, then it's called bare earth dam. So this is your bare earth dam, and this is your dam. So we can generate dam, bare earth dam from this dam. Once we have this raw DM data, we can generate the bare earth dam. What I use of bare earth dam to generate contours. Contours does not include the height of trees and buildings. Or if you want to study soil erosion, water flow, and so forth, it has very good applications. Second, for this is your forested area, and you want to study how this area looks when there is a leaf shed. So you can generate bare earth dam, and you can feel how the area looks when it is leaf shed conditions. In landslides, of course, slope is very important parameter in landslides, so that can be get well with very high accurate dam data. So we can have the landslide donation, landslide management, and landslide disaster estimation. And which area is more prone for landslides if the slope is playing role there. Then mapping glacier topography, as I told you, the space-bound Lidar was developed for ice sheet depth measurements and glacial studies. Bathymetric, as I told you, here it is using 0.5 micrometer wavelength, where you can get the water depth. So here what is happening, the first beam is giving you water top surface and second beam is going up to the water body depth, and both you will get both two returns. If you get, when you take the difference of both, you can get the height, depth of this water body. But here wavelength is 0.5 is used because 1 micrometer will be absorbed by the water. You can use for forest mapping for generation of bare earth dam, estimation of biomass volume. When you get the raw dam, so which is including your forest information, then you generate the bare earth. So once you get the bare earth, you have eliminated the tree biomass. So if you record the tree biomass which you have removed by generating dam to bare earth, so this tree biomass can give you the direct input to estimating the biomass of this forest. And it is possible nowadays. There are softwares. If you feed the raw data, which is including the ground and the tree height, you give the initial very seed information, the tree to tree approximate separation, approximate tree canopy, and approximate tree heights. Very approximate. If you give it, the algorithm can give you the very good output. How many trees are there? What is the girth of each tree? What is the canopy of each tree? And so forth. And with these parameters, you can easily go for tree biomass estimation. It's very good input in the forestry. Then here again, bare earth DM surface, and you can see in animation how the from dam to bare earth surface has been generated. Same way for here, Lidar terrain mapping in forest at different resolution. If you see, this is by USGS dam, which is available through satellite data. So here you don't see much detailed stream information, and the dam is not so much smooth. A lot of spikes is there. But here you can see the Lidar dam is very, very smooth. You can see the roads, other features very clearly. Streams very clearly in the Lidar data. Here. Again, canopy surface models have already shown you. Then here basically we are from the raw dam, we are removing the bare earth, we are just keeping the tree biomass, and there you can represent the canopy surface model, how the trees are there with respect to the canopy. Urban applications in generating the 3D city models, change detection to assess the surface structural damage to structures after a disaster, particularly after an earthquake. Drainage and other utility network is very, very important nowadays. Every alternative cities are going for flood issues, emergency in the route planning, other urban city applications. This is a case of 3D city model mapping in when the World Trade Center was demolished. There was a very big disaster in USA. So basically after that also very huge debris has been accumulated, and they have flown with airborne Lidar to see its volume, and they have estimated how much trucks and how much time it will be required, and from which area they should start removing this debris. This very, very huge debris of 2 twin towers. So this is one example of use of Lidar technology in Europe, this accident which was happening. Urban modeling, you want to see the building footprints, built up your auditoriums, you want to map them. Then I told you the wire antenna setup. So they want to know the location which is giving the maximum coverage, minimum blockage of the signal. So you can do view shed analysis from the different points, and it can tell which area is suitable for mapping for putting the antenna. This is basically line of sight example. Line of sight or view shed analysis, both. Mining estimation to find out the volume of in the open cast, how much volume is there for today to be excavated or to be removed, and on the ground you can cross check. They have done the same volume they have removed, or they have removed some extra volume as illegal mining is going on. These are cut and fill example. This area has to be cut and this area has to be filled. So you can do for line route alignment for road or railway how much cut and fill is required. Once you have the data, corridor mapping for different pipelines. One very unique important is application is for high tension wire. The companies which are distributing the electricity from dam from hydropower plants to the city, they have high tension wires of 1 lakh voltage electricity in that volume is transmitted from there. So every year they want to see the vegetation which is coming under this fire line. It's not close to the high tension wire because it can transmit the current to the ground. So they have to make it clear along these cables. So if you fly the Lidar with very small density of points, you can easily map the trees along these cables. You can see these blue lines are the cables, and we can see how much gap is there. Wherever the gap is less, you can take care. The company should remove these trees every annual 1 year or every 2 years interval. They have to do this exercise, and number of times companies are not very honest who got the contract to make this clearance. But through Lidar, we can do this monitoring. Yeah. So these are all the applications. So I just covered initially the conventional Lidar, conventional techniques for topographic data from ground to airborne to aerial photograph, satellite-based satellite photogrammetry, and then I went for advantage of Lidar and how it works. Its basic components is a laser sensor which gives you range, but range is not sufficient. You require coordinates from GPS to know the sensor location every per second and its direction, in which direction the beam is fired. If you integrate all these three data, you get the actual ground data. On the ground, it is a basically geometrical data, not the imaging data. But you get the point clouds very densely populated. So there also you can see the features, and if you interpolate, you can get the DEM or TIN or contour data. You can generate DEM, you already have. You can generate bare as DM, that means you are removing the ground features. And you get the bare, it has an application to generate the contours and so forth. Plus the whatever information you remove, you can use them to generate its parameters like building. If you are removing them, you can get the area of the building from that removed data, the length of the building, orientation of the building towards from north. It is single story or double story, that also you can extract. In the case of trees, you can map the tree canopy, tree height, and so many parameters. And then application I also talked about. Thank you. I'm reaching to 11:30. We have maybe 6 minutes for question and answer. I hope it went nicely. Now I can wait for questions.
Kindly post your questions on the chat box or raise your hand, please. Sir, there is one question from the YouTube by Krishna Dhuriya. Will it provide data for dense gaseous state? Example, if it can measure some explosions happen in any factory and can measure its extent.
Can you explain again the question? I did not.
In the chat box.
I did not got the question. Or you can you repeat again? Not clear to me.
Just I put in the chat box. Okay, I repeat it. Will it provide data of dense gaseous state? Example, it can measure some explosions happens in any factory and can measure it extents.
I think the question is related to some explosives can be identified from the industry.
Yes, sir. Regarding there is a blast.
No, explosive you cannot identify from Lidar. Explosive you cannot identify from the Lidar technology because it is giving you geometry measurements in the form of XYZ. Any measurements if you want to do like tree height, building area, building length or from north, that you can do, but not the explosives there on the ground.
Any more questions?
Yeah, Sab Yanchi Kabiraj has raised some hand for question, I think.
Sir, it's nice to hear you, sir. It's
Yeah,
first
thank
of
you.
all, it's a wonderful presentations from you, and we have seen the applications of Leader. So,
Yeah,
questions is, it's like Leader is a point data, and as you mentioned,
yeah,
and how it can differentiate the features, sir. For example, I am doing a survey in a forest area. Now, different species in terms of like different types of rhododendron or some other species, how it
yeah,
will like verify whether it how many different types of species are located in the same zone, or in terms of like features, like in generally we will do land is land cover, how it can find out the different features. So is it
yeah,
possible using leader data, sir?
yeah. So even you touched upon my applications where I'm basically applying machine learning also in the rhododendron or some like palas trees and maybe the in the forest like shisham trees. One of the PhD scholars working with me and on the forest species for like shisham and acacia. Now there are two things. Actually, one is you have to understand that are you recording the reflectance of the species like in the form of remote sensing data, you get the reflected energy, right? Now, in that case, is the one date is enough or you require temporal images? Because if you are going for specific species, you are not going just mapping forest. Within forest, you are mapping the species. That means you are going for level 2 or level 3 classification. Now, if you see for lidar is not giving you reflected energy. You have to see it is giving you tree heights and its tree girth. So you have to see the geometry of the tree of rhododendron, its geometry. If it is unique, and what is it that the geometry is defined, the canopy size, what should be the canopy size of 3 meter by 3 meter, and what is the average height of the tree, and all these things, if you can measure from lidar, then you can distinguish, and it should be unique because you are going for unique species. There should be no spectral overlap or geometrical overlap, because if you're talking about lidar, geometrical overlap should not be there. Same type of gut, same type of cropping should not be there for palas tree. If it is there, then both will appear like the rhododendron and you will say it is rhododendron. So you have to see spectral overlap should be minimum. So whenever you go for species level, level 2, level 3 classification, you have to see the overlap between these objects should be minimum. The spectral overlap or here geometrical overlap, because from lidar we are getting the geometrical information. So here you will not get the reflectance, you will get the geometrical information in the form of tree canopy, tree height, and its gut size you can get. If they are unique for rhododendron, then you can map. Otherwise, the second solution comes, which I'm experimenting, because LIDAR has so much limitation of data availability. If you don't have UAV, if you don't have sensor of LIDAR, if you don't have GPS on it, you can't get the data. Again, you are stuck. Airborne is restricted in the India, and the space base is quite limited to do that. So second part, I'm doing it basically from my PhD onwards for using the spectral information. Now when I use single date image, again it is limited because it cannot handle the spectral overlap. When I'm using the remote sensing image, there I have to see the spectral overlap, and that is very high from species to species. So if your signature is matching with my signature, I can do fraud in your bank account because it's matching. So that matching is avoided in the bank. Same way, when you want to avoid to have spectral overlap between other species, you can easily map. So there you have to avoid the spectral overlap. So here, with single image, it may not be possible. You have to go for multi-date, and in multi-date, if there are issues by single sensor, it may not be possible. Then you have to go for dual sensor or multi-sensor approach. So there are things which can work.
Sir, another question is there any like free leader data available in public for public uses and all, and any software for that?
Softwares are free, not full strength. What happened? Anybody has developed the software. So for the beginning stage of the software, they keep it free. Why? To get evaluated by the people and get the feedback at the beta level freely. So they keep initial software free, but once it is fully operational, then it's not free, because nothing is free in this life. Please remember. So when you ask free, you have to see why it is free.
So another
But Indian data may not be free for LIDAR, but foreign sites I've used which is free number of times. They make it free under some computation. So I get involved in the competition to participate, and I get the data to get evaluation. So I've done it to get experience and learn it. So lot of foreign sites, it is freely available on the net. You can download, maybe it can be airborne or it can be UAV based. But the satellite base is free. You can download from ISAT, and second one was Calypso satellite, which are now not working. But ISAT second satellite 2 is working. So there you can learn by yourself and process, and there are some tools and do it. Learning by
Sir,
self.
another thing is regarding the biomass. You have explained very well, and like one satellite data is GEDI,
Yes, yes, yes.
GEOI. Whether
Yeah.
that can be like it is open source, and how to use that, that I am not aware it.
I
Uh,
also not used it, but maybe with your promptness, pushingness, I may also think after some time to use our forestry department. They use it better. Get it done.
okay, sir.
Get
Okay,
it,
sir.
get it done.
Yes, sir.
But
Yes,
I
sir.
have not used that one. Yeah, but I've seen that it is giving you height information. But you have to be careful to use that height information if it is useful. But since it is designed, it is useful. But you have to learn by yourself, right?
Sir, is there any like remote? You have explained nicely about LIDAR, and is there any till now? Is there any like sensor which can like map the underground surface? Like, is there any wire underground or anything like
No,
underground?
does not give you penetration in the underground. For that, you have to go for, because it is not going to very hard, very large wavelength. So there you have to go for radar and choose the wavelength which can go for penetration.
Okay, sir. Up to what depth it will go, sir?
There, this is it goes up to 2, 3, or 5 meters. But from if you use it, that is space-based satellite. But if you are using GPR, that can penetrate around 40 meters or like that. But in the case of lidar, one way we can say penetration, but not for the ground, for water body. It gives you water depth. If you are using wavelength 0.5 micrometer as a bathymetric lidar, it can give you penetration up to 40 meters with the condition water should be clear. So if the water is clear, pure, not no any mixing of turbidity or algae, it can penetrate up to 40 meter. It can give you depth of 40 meter. If there is algae or turbidity, the depth prediction will come down. So for lakes, for rivers, and for coastal regions, you can fly on an aircraft and quickly can know its depth profile.
So another thing is you have shown some photos of like LIDAR data, and in that I have seen some color variation, like some highly elevated area in red, and then water body it shows somewhat like depth areas it was showing blue. So based on what like parameter it is dividing the color, sir? Can you
Oh, that
explain
is
it?
a pseudo color. You can give like generally like they say red is, you can take red as a very high height of the very large height of the tree. Then blue you can maybe yellow can keep medium height, and yellow can be, sorry, blue can be low height. So that is all pseudo color. Pseudo
Okay, okay,
color वो आपके ऊपर है, उसमें कोई स्टैंडर्ड नहीं है कि ब्लू
okay,
के लिए आपको वो लेना है.
okay,
That
okay,
is
sir.
representation of the colors कि अगर रेड कलर है तो उसका हाइट 40 मीटर 60 मीटर तक जा रहा है, 40 से 60 मीटर की रेंज में जा रहा है. और अगर वो येलो कलर है तो वो 20 से 40 के मीटर में जा रहा है. ब्लू है तो 0 to 20 के रेंज में. वो कोई स्टैंडर्ड नहीं है, वो आप अपना कलर कोड दे सकते हैं.
Okay, sir. Okay, sir. Understood, sir.
One question from the
Thank you, sir.
Krishna
Thank you, sir.
from YouTube. How the lidar is useful in a beam modeling?
How is lidar useful for
Beam modeling,
which modeling?
building information modeling, a new technology. Beam, BIM.
Beam modeling.
Yes, sir.
Building beam.
Yes, sir.
Okay, that means a core civil engineer is asking to design a beam of a building. You don't design the beam of a building because in civil engineering you have 10 subjects, 10 specializations, from structures to surveying. And from talking about surveying point of view to for measurement, surveying is there is for measurements in civil engineering. And if you want to go for beam designing, then you have to go use the expertise of structural engineer. So through structural engineer you can design the beam, not by the lidar. Lidar is used for measurement, not for designing. Of course, in railway engineering, you can do cutting of the railway tracks because it is used for metal cutting. It is used, not for design.
I think there is no more question from YouTube, and one question from Vallabh Ganguly. How often the lidar satellites can revisit the same area?
So because you want to know its repeativity or any other question is there in that?
So there is a repeatability of the revisit time.
Revisit time I don't remember because I used the ISET 1 data in 2005. I was having 2 students, MSc students, consecutive year. So I thought to integrate the ISET height data. It has images also, but I accepted only height data, latitude, longitude, and height. And then I was having point data from Cartoset. Actually, when I visited ITC New Zealand for 3 months, and that time there was a professor called Vandermeer Freak. He was young lecturer there, and now he's professor there. So he has given a lecture on interpolation, and he brought one guest lecture also on that, and he talked about different interpolation techniques, Kriging, IDW, and then other co-Kriging. And there he talked about that in co-Kriging you can take more than one variables. In Kriging you take only height, H1 of different points, but in co-Kriging you can take height from two different sources. That means, or maybe more than that. So that point was there, and he talked about application in mining. But in that thought remains in my mind, and after around 4-5 years back, when these students came, and I was thinking that now I have two variables. One height is coming from, and he also explained why co-Kriging has to be done. When you have samples of very poor accuracy, when you have large samples of very poor accuracy, suppose you are mapping CO2 in a city and you have a sensor which gives very poor accuracy of CO2, so you can take large number of samples from the sensor, but accuracy is poor. But you have certain data which is giving very less number of samples with very high accuracy. Now you have two types of sample data. In one case, you have large number of samples, but accuracy is poor. In second case, you have samples with very high accuracy, but very large, very few samples, or hardly 5 samples. 5 samples with very high accuracy and 100 samples with very poor accuracy. Now, when you integrate these two data, and there you have a interpolation technique. So this thing he explained me there, and I attended his class, and he taught application in geoscience for mineral mapping, which was developed. The Kriging was developed in Australia for mineral mapping interpolation. So this thought remains. When I came to know Cartoset data with ISET data, and I thought now I am getting two heights. Cartoset data I evaluated initially in 2005 when it was launched, and we published a paper. So after that, when one first MSc student I guided remotely, he came to the campus from Pune University as an MSc student. So then I have given the project that you can take a height from Cartoset data, giving accuracy of around 4 to 10 meters. But ISET data was giving you height of around 1 meter. So then I have integrated the two data. But it's repetition I am not aware. You can see on the net its specification at every watt days the same. The satellite is available in the same area. But there I explored its integrating through co-Kriging as two variables from Cartoset and ISET, and we found the accuracy of Cartoset when we added the few points from ISET. Its done accuracy was improved. Initially, we have done, I think, two things we have done. I don't remember the two differences, but we have experimented with two different concepts in the consecutive 2 days. 2 years rather, that was in 2005 and 6. And we published both the papers from the MSc students in ISRS journal. You can see ISET plus Cartoset data. If you search with Anil Kumar, and one person was Swapnil, and second girl, I don't remember her name. Yeah, we published these two papers in 2006 and 7. But it's a repetition you can find out. The points are very sparse. Maybe, and yeah, I've shown in one slide with the first slide itself when I was showing the different sensors. You can see I've already shown the plots here. I'll just share my slide. Yeah, here. Let me just share again once more. So here you can see this is the image which is talking about. So here you can see these are the lines coming up, the points acquired by the ISET data. And the difference across points is very large, it is of kilometers, and along the track it is of meters. So they are very sparse points. You can use them straight interpolation. So they are not very dense points. Dense point should be there, something where I've shown you again. Here I've shown you one more slide where the points are decreasing or increasing, maybe not in this slide, but I just shown here. Maybe I just is this right? Yeah, here. So here you can see the density of points will be very large. So to get the dam. So overall, this repetition you can of the revisit time you can get from the satellite. If you just type ISAT, its revisit time, you will know at what date it is available for the same area. But I don't remember. I'm quite poor in GK. And yeah,
Sir, another question
yeah,
is
yeah,
from my end. So the question is, we have used SITM DAM, okay?
yeah,
Then we have used Cartosat also, sir, which
yeah,
is like our ISRO, our Indian these things. So
yeah,
what I found, sir, there are like lot of missing data in Cartosat, and whereas in SITM we have not found that much error. And the thing is, while we are using Cartosat, we are getting the error like minus 270 meter, that type of elevation it comes. So how to rectify those errors? It is out of this like seminar questions actually, but
yeah,
as you are a IIS,
I got the point. Long back when I was doing masters, our professor Dr. I told when he was talking about use of stereo photogrammetry. So he talked about the case of stereo photogrammetry. Like he told, when you're sitting in India, you can get the data of Chinese terrain, how it is undulating. So if you take a full strip, because satellite does not give you data into small pieces, like from company, the cloth is coming not in pieces, it is coming in a roll. So data is coming in a form of roll, which is coming from China to India. So if you have a stereo roll, you can get the complete done from China to India, right? But still, that time technology was not there. When the Spot 5 was launched, having the stereo camera, and IRS satellite 1C, 1D was launched, later on Cartosat, the IS-1C, 1D and Spot was not having the orbital parameter to be used. They have developed the stereo data where you require your own ground control points to get the dam, right? But nowadays, if you see World View 2, Cartosat, and ComSat, and Claris data, they are not using GCPs, they are giving you data in the form of RPC. That means they are giving the relationship with ground control points to the satellite orbital parameters. And the foreign satellites, this relationship of RPC is very high, with a very high accuracy, because they are using orbital 6 orbital parameters and estimating with very high accuracy. So if you use the concept satellite and you just press 2 buttons using RPC data, within half an hour you can get a dam without giving DCPs, and the accuracy will be very high. I used with one of the SESTEC student, we had one course, and for 3 months he wants to use very high resolution images. So I got the free data of Spain, Barcelona, of ComSat, which is Korean satellite. And just when I process for them to generate the auto images for image fusion, their dam was very smooth without adding single GCP. I did not went to Spain, so they were having the orbital parameters related in the form of RPC. So that dam was very accurate, and then I added one or two GCPs from Google Earth. The dam further improved. But in the case of Cartosat, the orbital parameters are not so accurate. That's why when you process the data without GCPs, the dam is not so smooth. The moment you add GCPs, the dam becomes smooth. So that is the problem of orbital parameters, estimating the orbital parameters, because remote sensing means completely sitting in room without going to ground, you should get the measurements. So if you have very correctly, accurately accurate orbital parameters, you can use them to generate the dam. So you don't require ground control points. Can you think that when the US is fighting with Iraq, Afghanistan, they do a lot of GCP collection in Iraq before war? Is it possible in a month they can collect large number of GCPs? No. So they fly spy satellites, and they have very accurate orbital parameters of the spy satellites, which have been life of 2 to 3 months, low flying 300 kilometers, and they generate dam very quickly, and even the images of these areas very quickly for strategy planning.
right, sir.
So orbital parameters are estimated very accurately with these satellites. There is
So
a
is there
solution.
any is there any planning to give a good accurate data for Indian? Actually, we are looking for Indian satellite system by ISRO. They should be
I'm
having
looking,
like
the best satellite which is freely available. If you talk about stereo, is not freely available because it is more or less gone completely commercial. But few scenes can be available, can be used freely, like ComSat. I got sample data not for India, for Barcelona. But if you talk about in the remote sensing domain, Landsat is free, very beautiful data. It has gone from 8 to 9 series now with large number of bands, but 30 meter, you have to see it is useful or not, but not the stereo one. But when Sentinel 1 and 2 is freely, I'm using for last 2 3 years, I use extensively the Sentinel 2. Before that, I used Landsat, and now I'm using this Planscope Dove satellite, which is at 3 meter. For research point of view, it's free to me, and I'm exploring for the last 2 years continuously the plant scope data. But that is not a geometrical data, of course, it is spectral data. But one statement is coming up in my book also. If you talk about spectral, because you are trying to distinguish the different species or different crops or different water conditions, there you require temporal data. So when spectral information is not so much strong to give you the unique information of that unique species, that's why it is failing. You cannot use a single data image or even hyperspectral data number of times, the unique species from forest or from crop. So then I say when spectral information stops, makes a limitation to extract the information, you can use the time information. The line is when the spectral information stops, when the spectral information stops, the temporal information starts to give you the information. So there are different ways, different things you can use it from your data as per the suitability to get the information.
Sir, we are using Landsat, we are using Sentinel. Those are outside of our country. So, like we are using other countries' data.
Free to use.
Yeah, free to use. That's I understand. But what about our ISRO, sir? Indian satellite, what they are doing,
I
sir?
don't consider country into country. I see as a scientist which data is suiting and where I can explore and where something new I can get.
Yeah. That's why that I can
That's
understand, sir.
my thought and boundary. I don't classify when the wind flows. It does not check the country boundary. Please.
Yes, sir. Correct,
Sorry
sir.
for that.
That is
I
correct,
follow
sir.
nature, and from nature I got it that when we use mean parameter, it is a distortion to the samples. We should use the raw samples. If the doctor says don't drink juice, eat the fruit, because when you take juice, 20% juice is got waste. You have paid 50 rupees one piece of fruit, but when you eat the fruit, you take 100% juice and you take the fiber also. So always be natural and consume natural and use the natural samples to get the full information. And no boundaries in working. So I don't make any boundaries. I will not work with him. I will work with him wherever I feel. It is useful to me to explore. I explore at max time.
Sir,
And that's
I was doing research regarding soil salinity detection,
yeah,
and there I have used this Sentinel 2,
yeah.
and with the spectral band and machine learning. So machine learning in the sense like random forest, then SVM, then CART. These three models I have used. And do you think, sir, except these topographical parameters like elevation, slope, and
The
wind
indication is the
speed?
second resource person is ready, and we
Yes,
should cut down the questions. But salary I can give you. People have used much less remote sensing than ground-based information. You have to see how you can integrate and nicely you can extract the information.
okay, sir. So because of time bounding, I think I should stop. Sir, thank you for your valuable suggestions and information, sir. Once again, sir.
Yeah,
Thank
thank
you,
you.
sir. Thank you, sir.
There is no more questions, sir. I thank you, Dr. Anil Kumar, sir. We start from the scratch and integrate the LIDAR with the GIS, remote sensing, GPS. Even you, sir, explain nicely DEM, DSM, DTM. You also focus on the different methodology for surveying using a space technology. Even you detail explain about technical terms and measurements, accuracy, limitations with the best clarifications for LIDAR. Finally, you include the different, so many applications for the students who is working in the different disciplines. So we thank you, sir, for your spending valuable time for the participants. Thank you very much, sir. And now we hand over the session, or sorry, we study for the second session. Dr. Mamta Chauhan is here. Is it okay, ma'am, for you?
Thank you from my side and inviting me. Now we already the second person is there, Dr. Mamta Chauhan. Please listen to her. Thank you all. Yeah.
Okay, sir. Thank you, sir. Ma'am, shall we start?
Yeah, yeah.
Okay. Today's our another speaker is a Dr. Mamta Chauhan. She is presently working as a scientist at Geoscience Division of Indian Institute of Remote Sensing, IIRS, ISRO, Dehradun. She has completed her PhD in igneous petrology on carbonatics. After completing her PhD, she joined the Space Applications Center (ISRO) as a research associate. She worked on hyperspectral and high-resolution remote sensing planetary data to analyze and interpret the mineralogy and morphology of volcanic and impact features occurring over lunar and Martian crust, and understand the understand them in a petrological perspectives. Her work reflected to finding of indigenous water on the moons and discovery of the ash-flow caldera on the moon have been highlighted in a Moon Greatest Hits since 2000s, compiled by the Lunar Explorations and Analysis Group, Lunar and Planetary Institutes by NASA. Recently, she has analyzed imaging infrared spectrometer (IIRS) onboard ISRO's recently launched Chandrayan-2 orbiter is an advanced grating-based hyperspectral sensor. The data was utilized for the clear and complete characterization of OH and H2O and development of the new algorithm to utilize IIRS data for estimating per pixel's lunar surface temperature for an approximate value for the surface emissivity using infrared bands of IIRS hyperspectral data. If we list her achievements, the entire webinar time is licensed. Hence, I hand over session to the ma'am to educate the all participants. Thank you, ma'am, for joining us. I hand over sessions to you, ma'am. Thank you, ma'am.
Thank you. Thank you, sir. Thank you for the invitation. Uh, so, uh, to start with, I'll share my slides. So, is it visible?
Yes, ma'am.
Yes, madam.
Sir, is it visible?
No,
Not
madam.
now.
Just, just a second. Let me check. Sir, is it visible?
Yes, ma'am.
Okay. So, I will be talking about ISRO's mission, Chandrayans, their payloads and applications. So, before starting, I'd just like to have a few little brief about the moon. So, moon is the fifth largest satellite of the solar system, and it rotates around the Earth, and together with the Earth, it forms Earth-Moon system. So, Moon is very unique in its term of bulk density, sizes, and origin. It's rotate and revolve around approximately at the same time around the Earth, and its diameter is about a quarter of the diameter of the Earth, and it's forming its volume is 2% of the Earth's volume, and 1.2% of the mass of the Earth. And Moon gravity is about 1/6 of the Earth's gravity, and Earth Moon system, because of gravitational attraction within this Earth Moon system, they keep them in the orbit around common center of Mars. So Earth Moon system shares a common center of Mars. These are the physical parameters of the moon. Its mean radius is 1737 kilometers. Mass is, as I have already told, mass and volume, mass is 1.2% of the Earth, and volume 2% of the Earth volume, and mass is 1.2% of the Earth. Density is 3.3 as compared to the 5 of the Earth, and tilt is about 6 degrees. So equatorial tilt is about 1.5 degree and the orbital tilt is 5.1 degree. So together it is 6 degrees. So having very less tilt, there is no seasons on the moon. Surface gravity is 1.6 meter per second square, albedo 12%. There is no atmosphere on the moon, and the surface temperatures are very extreme, ranging from 127 degrees centigrade to minus 173 degrees centigrade. So this is the image captured by Galileo spacecraft in 1992, showing the Earth and Moon. So this is the surface of the moon. This one is the near side of the moon. This is the far side. The near side, the phase that we see from the Earth. Because Earth and Moon is tidally locked with the Earth, we are able to see only the one surface of the Earth that we termed as the near side. So near side and far side, there is a small dichotomy. There is a differences with regards to the crustal thickness and the appearance. The near side, as you can see, there are more dark patches. These dark patches we termed as mare. Mare are the basaltic plains, the plains that are formed by extrusion of the lavas. So most of the near surface, or you can say around 17% of the moon surface is covered with mare basalts, and these black patches formed by basaltic intrusion are termed as mare. Other than the mare, the rest of the moon, we can see the bright portion in the near side and far side. The bright portion is highland portion. The highland portion is comprised of the primitive crust, which is composed of anorthosite, a mineral. Anorthosite, calcium aluminum silicate. So most of the moon surface, that is 83% of the moon surface, is covered by primitive highland, that is primary crust of the moon, and the mare regions, the basaltic plains, are the secondary crust that are forming only 16 to 17% of the moon surface, and they are in form of black patches. And because they have been present over the large basins, that is large circular structure that is formed by impact cratering, they are circular in appearance. So these are the two physiographically means main geomorphological features on the moon. And the moon surface is covered by highly cratered, covered by large number of craters because of no atmosphere. The surface is covered by various depressions, which may range from very micro meteoritic impacts to large scale impacts. So there are circular features. So most of the surface is covered with impact craters, and which are more prominent on the highland region and less on the mare surface. So the first question comes, why do we want to go to moon? As I have told, that moon is very unique in terms of its bulk density, size and origin, and its formation is related with the formation of the moon is linked intricately with the Earth. Moon is likely to have formed by a collision between a proto-Earth and a Mars-sized body that was termed as Theia. That means at the earlier stages of the formation of the solar system, when the Earth was forming, when it was in proto-Earth state, a Mars-sized object, Theia, impacted with the Earth, and it threw the debris into the orbit of the Earth, which coalesced to form the moon. So this theory we termed as giant impact hypothesis. So origin of the moon is intricately related with that of the Earth. Moon, another important, moon serves as a natural laboratory for the planetary processes. Moon allows the study of fundamental planetary processes, volcanism, meteoric impact, and different gravitation environment. And that too in essentially in vacuum, because there is no atmosphere on the moon. No? Moon so is a keystone in understanding the process that shape the terrestrial planets, which have been largely erased on most of the solar system bodies, and because of the geological record, mostly on the Earth, have been erased, and only because of the surfacial processes prevalent on the Earth, that record has been removed. and that is in preserved state on the moon. So that's why we're going to moon. Another important thing is moon is the only planetary body from which we have samples taken from known locations, and so that remotely sense data can be calibrated and absolute age can be determined. For moon, we have data sets for geology, geochemistry, mineralogy, petrology, chronology, internal structures. So these data can unequated for any planetary bodies other than that of Earth. So by virtue of lunar samples returned from the known geological units, Moon provides the foundation for crater size frequency distribution chronology. This is a technique where we can find the surface of the planetary body based on the number of the craters that are present over there. So this technique has been developed to understand this to determine the surface age of a crustal body. So because of the sampling of the rock samples from the surface of the moon, it has been possible. Moon has affected the Earth and evolution of the life on the Earth in many important ways. Because a large body like moon going toward the Earth would stabilize the orbit of the Earth to provide equitable climate so that extreme temperature do not occur on the moon. Second, moon's tidal effect reduces the spin of the moon. And earlier it was at the time of the formation of the solar system and when Earth was formed, it was nearly about 4 hour period, and it has been reduced to 24-hour periods. And also because moon is because of tidal effect, it has been possible that life have means evolved from it had facilitated the transmission of the light from the that oceanic part to the terrestrial planet. So moon has very large effect on the life on this Earth, as well as it is stabilizing its orbit and providing equitable climate. So, talking about the lunar exploration, earlier before the invention of the telescope, people used to observe the moons from the naked eyes observation. Then came the telescopic observation period with the invention of the telescope in 1609. Where earlier observation used to be taken place, observing the various features present in the moons, and they used to means have different thoughts about the various features present. So they used to compare it with respect to the Earth because they were not having high resolution observation. Then later came the satellite exploration period, and that can be divided into pre-Apollo, Apollo, and current era. Pre-Apollo period was the period from 1959 to 1968, when earlier missions were planned. Most of them were robotic missions. Earlier were flyby missions, then the orbiter and lander and rover missions. So these were the various missions, Luna, and mostly these missions were mainly from the two space agency, from USA NASA, and another was Roscosmos from USSR. So these were Luna, Zond, Ranger, Surveyor, Lunar Orbiter. Luna 2 was the first mission that was sent by Russia, and then the erstwhile USSR to the moon. It was the first orbiter. Then Lunar 9 was the first mission that successfully landed on the moon, and Lunar 10 was the first orbiter. The Luna 2 was an impactor, Luna 10 was orbiter. Then came the Apollo era from 1968 to 1972, when Apollo series of missions, Apollo 8, these Apollo missions were sent by USA, NASA. Apollo 8, 10, and 11, 12, 13, 14, 11, 12, 13 was not there, 14, 15, 16, 17. So these missions were very important because they have resulted in sampling of the lunar surface rocks, and they were also the missions where crew when a human being first landed on the surface of the moon and carried these samples from the surface of the moon. So they were very important in bringing the sample. The samples were analyzed, and there were other sample missions also, but they were not manned missions. They were Luna 24, Luna 20, and Luna 16. They were robotic missions. They also brought out sample from the surface of the moon. These are the various regions, as you can see. These are the sites of the sampling on the lunar surface. This is the near side of the moon, lunar globe, and this is the region, oceanus procellarum, dark regions. So they have been sampled from various portions of the moons, and together they have sampled both highland and mare regions. Then comes a period of current era, 1990 to present, where other space agencies also send their missions. They were Hitin mission from JAXA, Japan Exploration Space Agency. Then Clementine from NASA, Lunar Prospector from NASA, Smart 1 from ESA, European Space Agency, Kaguya from NASA, and Chandrayan 1 and Chandrayan 2 from India. And then Chang'e series Chang'e missions from Chinese Space Agency, LROs and Grail from NASA. So, with time, with the increase, with the advancement in the technology and instrumentation capabilities, this missions, the the science that has come out from the analysis of the lunar samples as well as from the observation has improved our understanding about the moon. What was prior in the pre-telescopic era and what was in pre-Apollo era, and then with the present missions, it has further improved. How is it has improved? I will just give a brief glimpse about it. These are the examples of the lunar samples. This is the sample from the basalt and from the mare regions, and that has formed by extrusion of the basaltic magma from caused by internal melting of the in the mantle of the earth, that is partial melting in the mantle that is extruded on the surface of the moon in form of basalts. So because of the means exclusions of the gases or volatiles, it has resulted in this porous appearance. These are the brecciated material, breccia that has, because of the surface of the moon is not subjected to any geological processes. Only process there is impact cratering. The surface is being impacted by large impacts from impact of meteoroids and bodies from the asteroid circles. So it has resulted in churning of the and reworking of these the rock, whatever rock are there. So they are mainly in brecciated forms. And then anorthosite, that primary rock, the primary crustal rock that is composed of anorthosite, that is calcium aluminum silicate. And so these are the examples of the lunar samples. Now coming to the India's exploratory missions, for which I have planned this presentation. So India's space agency ISRO is responsible for the this planning and execution of this planetary missions on the moon. So first mission on the moon was Chandrayan 1 mission. It was launched in 2nd October 2008. It has opened a new era of international cooperation. Its main purpose was to expand the scientific knowledge about the moon, upgrading India's technological capability, and providing challenging opportunity for planetary research for younger generation. It was an orbiter and impactor missions, and there were total 11 payloads, 5 from ISRO and other 6 from other space agencies. So this is the Chandrayan 1 spacecraft, and this is the launcher, this PSLV C11. Its main scientific objectives of the Chandrayan 1 mission was high-resolution remote sensing of the moon in visible near-infrared, microwave region, and low and high-energy X radiations. Mainly, it was designated for preparing three-dimensional atlas of the lunar surface and chemical and mineralogical mapping of the lunar surface. For three-dimensional imaging, mainly it was through the camera, stereo camera that was available on the moon, and at that time it was the highest resolution camera available on any planet lunar exploration mission. So, and for chemical and mineralogical mapping, there were various instruments and hyperspectral missions and spectrometers. So, main aim was to find water on the surface of the moon, and finding new minerals, locating sites for future manned missions, and putting India flag on the moon. So these are the various payloads for the Chandrayaan 1. These I have divided them based on the main objectives. For mineralogical mapping, there were three instruments: High-C hyperspectral imager, and then SIR-2 from the High-C was from ISRO, and SIR was for from Munich, Germany. It was also a non-imaging infrared spectrometer, and MQ, Moon Mineralogy Mapper. It was a hyperspectral imaging spectrometer. So these all were aimed for mineralogical mapping of the moon. Then for chemical mapping, it was KICS from UK, from United Kingdom. This was for chemical mapping of the surface of the moons. Then for topographical mapping, there were two instruments from ISRO, LLRI and TMC, terrain mapping camera, and lunar laser ranging instruments. This TMC2 was 5-meter resolution stereo camera for providing high resolution image of the surface of the moons. And it was LLRI was a laser ranging instruments for giving elevation information. Then for water ice determination, there was a radar instrument, MINISAR from NASA. For radiation environment, there was a radon from Bulgaria, and magnetic field mapping. There was an instrument from SARA, instrument termed as SARA, for magnetic field mapping. Then there was for chemical mapping and volatile transport, HEX, high resolution X-ray spectrometer. And then there was an impactor, moon impact probe from ISRO. It was aimed for lunar atmospheric constraint measurements. So these are the important results of the Chandrayaan 1. Before coming to the Chandrayaan 1 result, I would like to tell you that earlier, when through the earlier exploration of the moon, that is the timeline that I have shown you, that from Zond mission, Ranger missions, before Apollo mission. So during pre-Apollo era, it was based on the observation what has been done through the earlier instruments, rovers and landers. It was observed and it was their findings that moon was a primitive body. Primitive in the sense it is not having any stratification in terms of crust, mantle, and core. That is internally that it is not differentiated. So after sampling of the Apollo missions, it was uh, the main findings were that moon is not a primitive body, but it is a differentiated body with having crust, mantle, and core. But it is an anhydrous, and there is no volatiles on the moons. So Apollo mission's notion was that after Apollo mission sample analysis, there are no hydration features on the moons. But after this Apollo missions, coming to the new or current era, there were some missions that have earlier missions that the lunar prospector that has mapped the surface of the moons using neutron spectrometer, that has given information that there are some hydration features of the moon. Then later on, this Chandrayaan 1 was designated. Chandrayaan 1, some of the instruments, that is MINISAR and NQ, Moon Mineralogy Method, they were mainly focused for the observation of the water features, or water in the sense OH, H2, hydroxyl observations. If they were present on the moons, they were mainly aimed for observing those features, whether it is not or there. So the most important findings from the Chandrayaan 1 was presence of hydrated lunar surface. That means OH or H2 molecule is present on the surface of the moon. And these are the various sources of the formation. It could be either exogenic or endogenic. Exogenic in the sense it could have been implanted on the surface of the moon from the cometary or asteroid impacts that may be present in the permanently shadowed region on the polar region of the moon, which are in some of the craters which are out means they are out of the reach of the sunlight because of less tilt of the polar portion of the moon. Some of the craters they are capable of preserving the cometary impact water that has been introduced to them from the cometary impact. So they could be external in source, and another source could be solar wind implanted. That because of lack of atmosphere, the solar wind that is the surface of the moon is subjected to the solar wind. They could implant the proton on the surface of the moons, and then they can result in formation of OH by binding with the the O component from the silicates of the moons, and then result in formation of OH. Then there is another source, endogenic source, that is a magmatic water. So these could be the two important sources of the water on the surface of the moon, and both the sources, both exogenic and endogenic, have been determined using the Chandrayaan-1 M-Cube mission. Chandrayaan M-Cube was an instrument imaging spectrum, hyperspectral imaging spectrometer, having range from 500 nanometer to 3000 nanometer. This is an example of OH and H2O spectra, which can be determined from its absorption at ranging from 2800 to 3000 nanometer. So it will, in this range, it will show an absorption feature. These are the OH, H2O, and water ice. So there is a slight difference between these three. So this, if this absorption is there, we can say for sure that the water is there. So this is the Chandrayaan 1 spectra. There you can see there's a slight tilt over here in the range of 0.5 to 3 micrometer, or at around 2.8. So this was a confirmation that water is there. So these are the results from the Chandrayaan-1, showing the hydrated lunar surface from both endogenic and exogenic. This is the global map of the moon generated from Chandrayaan M-Cube. This is, you can see the blue portion, and over there, this blue portion is indicative of the presence of hydrated surface on the moon. These are the examples from the radar data, mini-SAR, showing the some of the region of the portion of the this is the polar mosaic generated from the mini SAR data, and these are the regions where these are showing a high CPR ratio, that is indicative of the presence of some of the region in the Compton Bilkovich and Nabula Delis crater, where hydration absorption feature has been observed with some silicic and noretic lithology. This is the spectra of M-Cube. So both endogenic and exogenic water has been determined from the Chandrayaan-1 M-Cube sensor. So besides water discovery, which was very important, and another new important mineral spinel, and a new lithology, pink spinel anorthosite, has been determined using the M-Cube data. So this is the spectra of the M-Cube, which is showing the signature of magnesium spinel, and that has been identified in various lithologies as well as various tectonic settings, be it central peak of the craters, rim of the craters, and rim of the large basins, or silicic lithologies. And another chromium spinel has also been identified. So because of the wide spectral range, and because of the hyperspectral data of M-Cube, it has been possible to determine new mineralogy and lithology from the Chandrayaan-1 data. Another important findings of the Chandrayaan-1 mission was validation of the lunar magma ocean hypothesis, that says the surface of the primitive moon is composed of plagioclase feldspar that is present on the surface of the moon in form of the primary crust, and this is the spectra of plagioclase feldspar. So these are the lesions that has been identified as a location of the crystalline plagioclase feldspar that has been determined on and mapped on the global surface of the moons. And these were important findings because earlier missions have given their results in the form that plagioclase feldspar may be present or anorthosite may be present, but the only information they were having that because they can be identified because of their high reflectance. No clear spectral signature were identified earlier. So it was only because of MQ that clear spectral characterization. It has been proved that the surface of the primary crust of the moon is prevalent and it is forming it has been formed on the large scale, and that is validation of the lunar magma ocean hypothesis that says the surface of the moon is formed by floating of the low density plagioclase feldspar during the formation of the earlier differentiation of the moon. And another important result from the Chandrayaan 1 that it has proved that moon is geodynamically active. That there are examples of landslidings and mass wasting or mass movement on the surface of the moon have been identified using recent data analysis from TMC as well as LRO missions. So that these results were some of the interesting results that has come out from Chandrayaan 1 mission. Now coming to the Chandrayaan 2 mission, that was another second totally indigenous mission of ISRO. It was launched on 22nd July 2019, and it was mainly designated. It was a orbiter, lander, and rover mission, and it was mainly designated for uh, to test the soft landing capability of the moon and to explore south pole of the moon. These were the two landing sites that were mainly planned for the landing of the rover and lander. This is the lander Vikram, and this is the rover Pragyan, and this is the orbiter. But unfortunately, the lander Vikram could not land. So, but the orbiter is working till date, and it is giving its results. This is the launch and operation of the Chandrayaan 2. It entered in the lunar transfer trajectory in 2019, inserted into an elliptical orbit in 2019. This 20th August, 2nd September. Vikram lander separated from the orbiter, and then landing was attempted. And then, because of communication loss with the lander and then ground station, so it has failed to land. The orbiter is operational in the 100 by 100 kilometer orbit. Mission life is planned for 7 years. Its main objective was to develop and demonstrate key technology for soft landing and roving, to expand knowledge gained from previous missions. Most of the payloads in the Chandrayaan 2 missions are miniaturized version of the Chandrayaan 1 missions, and they were mainly aimed for lunar crustal study for topography, seismography, lunar surface, chemical composition, thermophysical characteristic of lunar regolith, and composition of its thinous atmosphere. And to identify and to go for surface composition and mineral identification and mapping at global as well as regional scale, and three-dimensional mapping of its lunar regolith, measurement of near-surface plasma environment, and study electron density in lunar ionosphere, and study water molecules and understand its distribution using the various instruments available in the various fields. And it has the highest resolution camera, OHRC. I'll come to the various instruments. These are the important payloads of the Chandrayaan 2 missions: imaging infrared spectrometer, that is hyperspectral imaging spectrometer in range of 0.8 to 5 micrometer, and it has an extended range with respect to the earlier hyperspectral imager MQ missions, and this extended spectral range was mainly planned to observe the hydration feature clearly. Because of termination of the spectral range of M cube at around 3 micrometer, it was not possible to see the clear spectra of the hydration feature on the moon. So this IIRS spectrometer was mainly designed for observing that hydration feature in complete perspective. Then there is a orbital high resolution camera. This is the highest resolution camera, having a resolution of about 0.3 centimeter. And this is terrain mapping camera, stereo camera for surface mapping. And then Chandrayan is a large X-ray spectrometer class for chemical composition determination, and then solar X-ray monitor, dual frequency synthetic aperture radar for radar observations, and Chandrayan X-ray atmospheric composition explorer, Chase 2. So all these instruments are mainly advanced and miniaturized version of what were available on the Chandrayan 1 missions. These are some of the earlier results from the Chandrayan 2 missions. These are this is the Mare Oriental regions seen from the Chandrayan 2 lander camera at about 2,650 kilometers away. Here you can see the various secondary and primary craters on the of the Mare Oriental region. This is Apollo Basin and this is Mare Oriental Basin, and these are its various primary and secondary craters. And this is the OHRC highest resolution camera of the moon, from where we can see the various tiny features on the moons and even very small uh, boulders and small ejecta particles on the surface of the moons in very clear perspective. And this is the example from the terrain camera mapping camera TMC2, showing the relay region on the moon. And this is the that is DEM data from the TMC, showing the depth perspective of the various features on this portion of the moon. This is the wrinkle ridge dorsal gradient, as observed from the TMC2 data. These are the DF SAR images from the dual frequency radar data, and they are showing what could not be observed from the optical observation could easily be observed from the SAR data. And this is the results from the Chandrayan 2 IIRS spectrometer. So this is, I have earlier shown the water signature, how to in the spectral range, how can we observe the water, how can we characterize the water. So this is the spectral signature of the water, which showing absorption of the water, OH, and water ice at around 2.8, 2.9, and 3.1 micrometer, or 3,100 nanometer. So this is a nanometer. So this is the M-tube observation of the water, and this is because of the thermal issue and because of its termination at around 3,000, it could not be clearly observed. Over this only this curvature and this absorption could be observed. The complete picture cannot be seen. So using Chandrayan 2 IIRS data, it gives the capability to observe this particular feature in clear perspective. So this is the absorption of water from the Chandrayan 2 mission. These are the forthcoming lunar missions from India as well as from the other space agencies. Chandrayan 3, it will be a lander and rover mission, and it will be mainly targeted for landing over the surface of the moon. And this is ISRO's JAXA mission, lunar polar exploration mission. It is also a rover mission designed for the south pole of the moon for polar volatile mapping. And this is Artemis human space flight mission from the NASA, then NASA Capstone mission, and also another volatile investigation mission for polar exploration, Viper mission. Then there are other Bearship from Israel, Luna 28, Hercules. So these are all the future missions that are mainly targeted for the South Polar region and volatiles explorations. So if you want to search and explore the ISRO's data, you can go to these websites for downloading the data from the Chandrayan 1 and Chandrayan 2 missions. So ISRO's Space Science Data Archive, and this is Pradhan site, so you can get the data. And these are the ISRO's Moon Atlas, okay, that has been compiled from the Chandrayan 1 data that are also available from Lidar sat site. So you can download this atlas, and you can see the what now observation mainly through the high C and TNC has been for the various features of the moon has been compiled in this atlas. So this is the end of this. So these are the sites I have also told earlier. These are the sites from where data can be downloaded and it can be analyzed for their mineralogy, morphology, and chemical composition from whatever perspective you want to study the science of the surface of the moon. So that is all about the India's missions and their findings. Thank you.
Thank you, ma'am.
Thank you, sir.
If
If
you
you
have
have
any
any
question,
question, you are welcome.
So, ma'am, it's like wonderful to listen you. I am myself Sabyasachi Kaviraj from Anna University, Tamil Nadu. So the thing is, my question is, what makes very important to moon to every country? What is the main thing why this all countries are looking on moon? What is the main reason behind that? Why crores, like millions of dollars, why they're investing on that?
Actually, besides scientific exploration, for resource exploration also, mainly helium-3 that can be utilized as a future fuel. So they are planning, moon has been targeted for resource exploration. Then as a landing site for as a solar, you can say telescope for observing all other solar, means planetary features or solar system features more without an atmosphere, so it can be used as a laboratory, future laboratory. And also for if you want to go to beyond means solar system and for other planets, so it can be established as a laboratory over there for as a means gateway to the other planets. So for resource exploration, for other important experimental purposes, and for scientific purpose. So they are because it is very close to the Earth and it is an atmosphere-less body. So there are many advantages to going to the moon. Uh, mm, uh, uh, so being set as a site where we can means we can use it as a station to go to further another planets also. Okay.
So, ma'am, always whenever we look into the like moon's surface photos, it appears like ash color. And is there any vegetation till now we have found out in the moon, or what is the reason behind that? Why we are not able to find out the color like Earth? What is the reason behind that?
You're talking about vegetation.
I'm talking about the all colors which are present in the Earth, but it is not like in single color. Whenever you are showing that moon picture, satellite pictures, it appears as color. I can't see the difference color, like in FCC
Because of
comparison
lack
or
of
whatever it is.
atmosphere. See, on the surface of the earth, we can see various types of features and colored features because of the presence of atmosphere and variability of the surface features in the moon. Moon is atmosphereless bodies, and there are means not that much. It is variability is there over its surface. As I have shown you on the surface, mainly it is means. Featureless, only the main dominant features are the craters and basaltic plains. So, as compared with the Earth, less variability is there. Okay, on Earth, besides the Earth's makeup, the crystal, there are other surface features are over there. Various landforms are there. So that variability is not there on the moon.
Ma'am, you said that you found the water on moon, like
Water,
oh, small,
see,
but
water
very
is not
small,
that,
right?
yeah, that water is not that water that flow on the surface of the, that is
Okay.
hydration feature. OH and H2, earlier it was thought that water is not there. It is the minerals that are formed that are totally anhydrous, right? But now with the new findings and the precision in the experimental technologies also, and with the new observations also, we came to know that OH and H2 are there in the molecular form on the surface of the moon. Like earlier it was thought that it is totally dry. So that water, molecular water that may be present in terms of that is fluid inclusion or melt inclusions within the mineral, as well as the surface volatiles that may be present that may be forming very thin micrometer layer of OH and H2, right? Not that water that flow on the surface of that type of water is not there.
Okay, thank you, ma'am. Thank you.
One student from the YouTube, Mr. Vaibhav, asking, what is the cost of the satellites?
What is the
Cost, price, manufacturing cost.
cost?
Yes, ma'am.
They cost in crores because many of the instruments, I mean, payloads, they can consist of various high resolution cameras and all those uh, components are there. They are means uh, they are very costly.
Mr.
In,
Chirag have
Mm,
some question.
Ma'am, one question is, what are the mineral, important mineral till now we have found out in in moon?
on
Important
the
mineral.
moon, yeah. Minerals, mainly minerals, the dominant mineral are plagioclase feldspar, right? That is calcium, aluminum. Mainly silicates are there. Means better to say, mainly silicates are there. Calcium, aluminum silicate. Then there are magnesium and iron silicates are there in form of basalts. Then there are titanium bearing minerals are there, and pre-silica, that is pre-silica in the sense like granitic rocks are less prominent, although they are earlier they are supposed to be absent, but now with the new findings it has been found that they are not rare on the moon, but this type of feature. So in terms of mineralogy, mafic silicate minerals are there. That is magnesium, iron, and calcium bearing silicates are mostly predominantly present, and besides silicates, oxides in terms of spinels and ilmenite, that is titanium oxides, magnetite, they are there,
Ma'am,
right?
what you are thinking that, for example, like some minerals present in Earth also, whatever you said that all the minerals are present in Earth also. So what you are thinking that what way it will change? It will be like change in history, like we have found something new, like new discovery, and which will be useful for future. So what are the things like scientists are thinking that what can be possible like this mineral, particularly this mineral, will be important, and it can be possible like it may be
See,
possible like that way.
See, through minerals, we try to understand what it what could be. See, on Earth also, we cannot go too deep of the Earth. Or it is mineral is the only possible way to understand what are the composition of the Earth. So, the same way, using the mineral, we are using them as a window to understand what are its main important composition, and how this composition is different from that of Earth, and how it has evolved, because various that is compositionally it has been found that through isotopic composition and chemical composition analysis it has been found that moon has similarity in origin with the earth. So some of the minerals are there on the moon, but that are similar to the earth, but some are showing some differences. So in differences in the sense the abundances. So how they are, why they are more abundant on the over there? Why? What is the possibility? Because Earth composition, Earth crustal composition is mainly granitic, right? But Moon's crustal composition is anorthositic. So why is certain minerals are more abundant? Why certain minerals are less abundant? How we have started initially from the same point? How now we are differentiated? So, in order to understand that whole that process of differentiation and fractional crystallization, how the minerals earlier, what could be composition and how it evolved with the times. So, in that way, that is important. And also, if certain minerals are of economic importance, that can be utilized for economic purposes. So, the study of mineralogy is important.
Okay, ma'am. Okay.
One student asked in Google Meets, what is the possibility of the comets and asteroids collide or falling on the moon by Chirag?
Possibility, see, the moon is because there is no atmosphere of the moon. It is no means every time it is being bombarded by various meteorites and asteroid samples. So possibility there means that it is prone to that impacts. Still, impacts are going at micrometeorite levels. So because of no atmosphere, there is always a possibility that it will be struck by impacting body asteroids or comets if it happens to come over there.
Any questions? There is no questions on the YouTube live chats. Yes, Chirag? Okay. Thank you, ma'am. There is no more questions. Ma'am, you start from the history about the moon and so the latest sensors designs by ISRO and your hard work is really showing regarding the moon walks and the remote sensing. Thank you, ma'am, to enlightening the students.
Thank you,
Now we
sir.
are at the end of this today's webinar. I hand over my session to my colleague Akanksha Verma for vote of thanks. Thank you, ma'am, for spending your valuable times in small mistakes in the posters. Yes, Akanksha, hand to you. Your mic is off. You are not audible.
Ma'am, sorry to interrupt. The one question is, you have showed that heat map, like for example, land surface temperature in like lunar surface. Is it that data is available publicly, ma'am? For that?
Can you repeat your question? Sorry, because there is rain. It is raining in Dehradun. I am not able to hear. Just repeat your question.
Ma'am, you have like you did in the beginning itself. I heard that you did land surface temperature modeling for lunar surface, right, ma'am?
Hmm.
So that data, is it available publicly, ma'am? How to like derive, like we have used Landsat for Earth, like thermal images and all. Whether it's available for lunar as well, ma'am?
Yeah,
Publicly free data.
you are talking about mass wasting and all
Yeah,
that. No?
yes, yes, ma'am.
Yeah, data is available. You can use high resolution images. So high resolution images in the sense for Chandrayan 1 and 2 TMC data is there. From LRO's NAC data is there. Narrow angle camera data is there. That is 0.5 meter resolution. So you'll get very high resolution images.
Ma'am, which website, ma'am? That website you have just shown that one.
That website for planetary data of other missions. You can go for NASA's mission. You can go to Lunar Orbital Data Explorer, and for Japan's that Salim mission data, that is also very good data. 10-meter resolution TC camera data that is available on JAXA's uh, that website, Japan Saline
Okay.
Data Explorer, right?
Okay, ma'am. Is it like thermal image, ma'am?
No, they had high resolution images. For thermal images, if you want to go for thermal images, IIRS data is there. Then for NASA's data, Diviner data is there from Lunar Vital Data Explorer, and the thermal data, Diviner data is available.
Ma'am,
From
what is the range minimum to maximum temperature in Chandrayan, ma'am? Sorry to ask you again the question, interrupting that.
temperature
Like
in the sense,
temperature range, like minimum, maximum. What is the like? It is like Earth, or what is the like? What is the condition there?
okay, moon is having extreme temperature. I was already told 127 to means plus minus beyond 100, 127 degree to minus 123 degree. So it is temperature are extreme.
Okay, so
Pretty
those
hot.
things, whether those things can be captured by our thermal imagery, ma'am, whether
Yeah,
is
temperature
there
maps.
any
Yeah, temperature maps you can generate from IIRS data. Temperature map you can generate from
what is the
minus.
limitation in a sensor, in thermal sensor? What is the limitation? Like up to what 10 degrees centigrade
See,
you can measure?
yeah. See, for thermal, you can go for thermal range that is beyond 3.5. You can go for thermal capturing thermal emissivity. So for emission, you can, beyond 2.3, you can use any of the sensor that is having the range beyond 3 micrometer or 3.5 micrometer. You can use. So only those two instruments that I have told you, IIRS and Diviner, that can be used. That data can be used that are in thermal range.
Okay, ma'am. Thank you, ma'am. Thank you.
Okay.
Akanksha, up to you. Your mic is still off. I think she is facing technical issue. Yes, your mic is on now. Okay. Uh, behalf of the ISTAR College, ISG Vallabh chapter, I'm thankful to you, ma'am, Anil sir,
Thank
our
you.
director sir, our chairman sir, CVM University, my colleague Akanksha Verma, all the participants who make this webinar very successful directly or indirectly support to us. And very special thanks to both the speaker, Mamta ma'am and Anil sir, for spending valuable time for us in their holidays time. Thank you, ma'am.
Thank you. Thank you, sir.
Hence, we complete the session and I'm going to stop the meetings. Thank you, everyone.